And we are now recording from the current slide. Now, before we get into this and the projection comes on, I didn't realize it until today's faculty meeting that we have a celebrity in our midst. Sarah is on the most winning volleyball team we've ever had at Lawson State Community College. The last two seasons, they've set records for number of wins, and this year came so close to going to the Nationals. One game away from going to the Nationals. So that was way to go. All right. Any questions? Any other announcements of any nature? Okay. Did have a couple of people come in to make up some tests. Let me give you an update on this. I'm now been able to proceed some with the grading, but my word, it's been so difficult. I've had so many students in the last several days come in for registration when in my office hours. I only have a very few office hours, so they sort of shot a hole in my grading today and the last time. But tomorrow, as far as I know, I have 4 hours of office hours, unless somebody calls a meeting or something, and then hopefully I can get a lot caught up then and over the weekend as well. It's supposed to turn cold, so I probably won't be going out as much, so I'll try to get caught up. Way behind on putting grades on Blackboard. In fact, I can't even think if I got any of your grades on Blackboard yet. But I'll hopefully over the weekend be able to get maybe that far so I can put some in. I'm whittling down the stack, but I let it get way too big because the spring schedule is such a mess. But I've got just a couple changes to make to that tomorrow. But that won't take long, knock on wood. Okay. Any questions? All right. Now, where we left off Tuesday, we were doing technologies, energy sources for tomorrow, and we were on solar technologies, and we had just about to get to the power tower. Okay? Now, what a power tower does, it focuses light from the sun onto a pipe that either contains water or some other liquid that heats up and then later will be used for steam generation. It's not always in a tower, sometimes it's horizontal. When I was back at Georgia Tech for grad school many decades ago, they had one on part of the campus. It was horizontal. As you walk to class from the new part of campus to the older part, you walk right past this huge, it was like a trench, but above ground, and they had the mirrors there and focusing the light on the pipe running through, heating the water or whatever was in the pipe for steam generation, using totally solar heat, solar source, completely renewable, completely without any danger or harm to the environment. Okay? Now, there are other things that we can do. Sometimes I drive my wife crazy, I think, with some of the things I do. But you can do passive applications, use designs to use solar energy flow naturally. My father had a first cousin who married an architect. They've both been dead for a while now. All three of them have been dead for a while now. But way back, when he was designing buildings and could get away with it, he faced them south and had a large overhang as an eave and on the roof, and had the roof just going one direction, large overhang, and he put it at the latitude of that building, so that in the summertime, the sun was above that in the hottest part of the day, and you had shade. And by the way, mostly glass in front here. Mostly shade, so that the building wouldn't heat up from the sun coming in. But in the wintertime, when the sun dropped below the latitude, and that's the maximum altitude of the sun is right about your latitude, and then the sunlight would come in and warm the building. So it was a real nifty thing to do way back before any of this stuff became popular. Okay? But using designs to use solar energy flow naturally. How I drive my wife crazy is in the summertime. Well, whenever we have the air conditioning on, I get up in the morning. When I get up in the morning, I go around and open the blinds to keep the sun from coming in the summertime. And in the wintertime, I lower them just enough to try to maximize the amount of sun coming in when we're on heating mode. So it sort of drives her nuts because it probably doesn't make a lot of difference, but it makes me feel good. I'm doing all I can passively to use solar energy the best I can, or block it when I need to. Now, there are other active applications, and really, I don't know why every house in the U.S. doesn't have this. A hot water heater on the roof, facing south, okay? It's not really a hot water heater. It's sort of like a radiator in reverse. It's a series of pipes or grids or whatever with water pipes, probably painted black would be ideal, and the water is cycled through that, and in the summertime especially, but any time during the year, the sunlight hits that, absorbs the heat, and then that feeds into the hot water system. If every house in the country did that, especially here in the southeast where we have so much excess heat, especially in the summer, spring, fall, we could probably cut hot water bills big time. I'd say more than half, okay? Wintertime, not so much, of course. If it gets really cold, of course, you would have to make sure that the pipes didn't break. But we have very few days where that would occur here in the southeast, okay? So, solar collectors to heat water, heat air, or heat some other liquid that then is sent through and, well, used for hot water is the main thing. You could send it and pipe it through the floors and heat your rooms that way too. I think just for hot water, heater would be better. Okay, then, used for heating, or if you have enough of it for electrical generation. But basically, just an active application in your home such as that would not be generating any electricity. Okay. Now, here's one that is rapidly growing, wind energy technology. The wind turbines generate electricity, and wind is often inconsistent, but man, there's some parts of the country the wind blows strong just about all the time. I was in the San Francisco Bay Area for 3 years in the Navy. Every time I was in San Francisco, the wind was blowing like crazy. They call Chicago the Windy City. I don't know if it can beat San Francisco, because the West Coast, there's nothing to block those prevailing westerly winds coming off the Pacific, because the Pacific is wide and flat for miles and miles and miles, hundreds or thousands of miles, nothing to block the wind, and it comes and hits the West Coast. So big wind farms out there along the coast. There are other places, like I think I told you before, when my wife and I were in, she had meetings in near Salt Lake City, Park City, I think was the name of the town. It was one between spring and summer terms, or between summer and fall. And it was that week I had off, so I went out with her, and we drove around and saw some of the country we hadn't seen before. Parts of Montana, parts of Idaho, parts of Wyoming and Utah, little four-corner area up there, and saw some amazing wind farms, okay, producing electricity from that free wind. Okay, of course you have to build the towers and maintain them, but otherwise, absolutely free. Okay, and true, the wind's often inconsistent, but if you have other mechanisms to be producing electricity, otherwise it can certainly contribute to the electric grid. Biomass, okay, we've already talked about that some. That's plant material, mostly, and here's Justin. Does anyone else come in while I wasn't looking? Okay. All right. Plant material formed by photosynthesis that you use to produce heat burned directly or converted to other fuels. I think I mentioned before the using of spent cooking oils. Those can be cleaned up just like they clean up motor oil and reuse it. They can clean up cooking oils and then use that for fuels once they're through with the use as a cooking oil. Now, this one's a little bizarre. Agriculture and industrial heating, the use of sunlight to dry grain rather than having to expend fossil fuels to dry the grain to cure paint. I thought everybody did that, but I guess in some applications not. Yeah. Seems a little weak on this. Probably in the book it will tell you a little bit more. Now, some of these I found a little more out there, you might say. Ocean thermal energy conversion. Using the temperature difference between the surface and ocean depth to generate electricity. My word, that seems like not a lot of difference in temperature, and how would you make that very cost effective? I don't know. So I don't know enough about that one to comment. But something that seems a lot simpler to me than that, how about the use of tides? The tides come in every day and the tides go out every day, twice a day, every day. Could we not use that to turn turbines? Wouldn't produce a lot, but in some areas, that's a pretty big tidal difference that you have there. And you could use that, and it happens every day. Day or night, night or day. So you could, it seems like to me, we could take advantage of that. And it seems like that would have a lot more potential to produce more electricity than temperature differences in layers of the ocean. But I may be wrong. I don't know anything about that technology to even comment. Geothermal energy. And we talked about this before. And some of these percentages on here are hard to follow. Okay? Hot, dry rock, okay, is 85% of the geothermal energy. Okay? That's not a lot. It's a small chunk of our energy consumption, but 85% of that small chunk comes from just hot, dry rock. That's associated with volcanic activity. We sure want that rock to be dry, not melted, okay? And I mentioned Iceland. I did finish that story, didn't I? Iceland, very cold country, very, very cold country. You would think their heating costs would be exorbitantly high. They're not. Almost zero heating costs for any house, any business in the country of Iceland. Why? Because they're on a volcanic rock. That's what Iceland is. It's an island in the Atlantic Ocean, and it has a hot, dry rock not far below the surface. What they do is drill down into that rock, pump water through it, and then pump the water under the streets, into people's homes, into businesses, and they get all their heating from that. All the heating. In frigid temperatures outside, homes and businesses are very toasty, not using a bit of fossil fuel. Okay? Pretty amazing. But there's just not that many places where you have that near the surface. We ought to be using it everywhere we can. Now, there's others. Geopressurized resources, underground reservoirs of hot water containing natural gas. Okay? Now, which is the resource, the hot water or the natural gas, or both? Probably some of both. What comes to mind when I see this are things like the geysers in Yellowstone. Well, those are tourist attractions. They're not used for generation of electricity by any means, but there could be situations like that that you could take advantage of. And they say this accounts for 14% of our geothermal energy. So you see the two of these together, 99% of the geothermal energy. The dry steam, and again, this will be coming from somewhere very deep underground, very rare, only 3 sites in the U.S. When they say dry steam, that means superheated steam, incredibly high temperatures, okay? And use that to turn turbines free. It's done by the earth. Now, I don't really understand where their hot water, it doesn't seem to fit in here, but maybe it does. Hot water makes up most of the recoverable geothermal resources. In other words, you're heating water here. Basically, this is hot water here. This can be used to heat water, or just use that dry steam just as it is. But that makes what? You converting the heat, storing it in water. It can be circulated, as I said, in Iceland, directly into homes, businesses, farms, and so forth. So that's the best way to use energy like that. Just like I said, on your houses, if you had that grid of reverse radiator, basically, that was absorbing the heat from the sun, on the south-facing side, you can heat water and then use it. Have that supplement in your hot water heater. Many times during the year, especially here in the southeast, I would guess you'd have to waste some of that because your water would be too hot for you to use. It was just, you could collect so much heat from the sun that way and not use all the hot water. All right. Did I leave the previous one there long enough? No one said anything. Anyone? Do I need to go back? What's that?
I'm still writing the last one.
Okay. How about the one before that? Did you get it all?
I didn't get the.
Okay, I'll go back. I'll let you finish this one and then go back.
Okay.
Okay. Any thoughts on any of these? Let me just tell you a little bit other things we've noticed in some of our travels. We traveled through a bit of Germany. This was several summers ago, and we're just absolutely amazed at how many. There were some towns that it looked like every building in town had solar cells on their southern-facing roofs. Houses, barns, garages, whatever, they all had solar cells, on the top of the buildings to try to capture sun and produce electricity that way. And I thought, goodness gracious, why aren't we doing that? We have lots and lots of areas of doing that. There's another thing, and the problem is we have entrenched mentalities in our businesses and stuff, as in the power generating companies. Okay, you've seen these big tracks where they have the high voltage power lines going through, right? They cut down all the trees anywhere around those. They want no trees falling on the power lines, and keep it mowed and keep it cleared. In my mind, why is every one of those towers on the south-facing side got solar cells that augment and feed into the grid? I don't see why we don't, okay? There may be a reason, there may be an economic reason that maybe they're not efficient enough, maybe to convert the solar cells are DC, the power lines are AC, maybe that's the problem, I don't know. But it seems like to me, there you have wide open space, lots of it. Why aren't we taking advantage of the sun that's coming down on those towers? Got it? You need to go back one? Okay, sorry, I went too fast. Okay. And I'm sure there's tons of other ideas like that people, and you just wonder, why are we not doing this? Now, one of the things, I don't think it may happen, but it was one of the things being talked about in the campaigns that were leading up to Tuesday's vote. There were a couple of the ladies, I'd met but two of them, and worked with one of them actually on some other issues, who was running for Public Service Commission. And they were asking, why in the world are we not encouraging people to contribute to the grid, either by solar panels or wind turbines or whatever. But basically our homegrown industry here doesn't want to do that because they want to be the power generator and they want to control things. They don't want to have to pay people if they're coming up with ways to contribute to the grid. So in fact, they're trying to discourage them from them saving money by doing it. They actually tax them or charge them to generate electricity. Doesn't sound like a good plan to me. And maybe over time that will change. All right, we got this one. Now let's look at hydrogen. Remember that was one on the earlier slide. The energy storage and transport system, that's the problem with hydrogen. That's the biggest problem. Where are you going to store hydrogen? It's very light gas. It doesn't occur naturally as hydrogen in the natural ecosystem. It's all over the place. Every drop of water, 2 parts hydrogen, 1 part oxygen. Now that's not by weight, that's by atomic thing, H2O. Every acid starts off with H or H2. Hydrogen's everywhere. All your bases are OH, okay? Hydroxides. Hydrogen is everywhere. Every organic compound we have has tons of hydrogen. Well, lots of hydrogen in it, okay? But you see, that's the problem. Hydrogen is very reactive. It's going to combine with something. It doesn't exist as H2 gas very much, very often at all. It always is reacting with something else. So therefore, you have to generate the hydrogen to use. And how do you generate it? Most of the time it's through, if you're using water, you have to electrolyze water. In other words, put electric current through it, catch the hydrogen on one tube and the oxygen on the other tube, and then keep them separate because they'll explode if you get them together. But that costs as much energy, in fact, more energy to separate them than you'll get out of burning them. So that's not very practical. How do you store it? Well, very difficult, because hydrogen, being the lightest, smallest molecules that we have, and atoms that we have, they will go right through tubing, junctions, and things. They leak like crazy, okay? And they're very flammable, so you don't want the leaks going on. Those are the problems with it. And because it's the lightest gas, it takes up such huge volume, the only practical way to store it is under pressure. The more pressure you put on it, the more likely it is to escape, okay? And the more likely to have leaks. And the more likely to explode, okay? What's the advantages? It's just about the cleanest combustion ever. And we talked about this before. What's hydrogen oxide? Water, H2O. When you burn hydrogen, that's the result. Not carbon dioxide, not any other oxide, water. Okay? Can you get any cleaner than that? So what are the possible problems? Well, besides these we listed here, the best stored as liquid hydrogen. The trouble is, to get hydrogen into a liquid, you have to drop it to incredibly low temperatures. And therefore, you're spending more energy keeping it cold than you are using it. Okay? And then it's extraordinarily flammable. So you can't have leaks, and it's so easy to leak because in a rubber tube, hydrogen will just almost go through like a sieve because they're such tiny molecules. I'm sure you can improve on the rubber somewhat, but still, and anywhere you have a leak, there's a potential explosion right there. All right. Now, that is the last slide. I will say this about hydrogen that I don't mention here in the text. There is another way that hydrogen is done, and this is what they call fuel cells. Now, other things can be used for that, but what you do is chemically use something that has hydrogen in it. There's lots of things with hydrogen in it. Chemically get that onto your fuel cell, and through some process separate the hydrogen, and then immediately use it. So you don't have to store it. You don't have to pressurize it. You don't have to cool it. Use it immediately. That's what makes a fuel cell, okay? And those are technologies, I'm sure, that are being worked on. But here again, and I hate to sound sort of negative about it, but I grew up at a time where a lot of things were suspect. And there's just this aggravating inkling in the back of my mind that the big power brokers, not talking about energy power, but power brokers, they all sat on each other's boards of directors, and they have this really close-knit, I can't think of a nice word to describe it. They feed on each other. So and at one time the car companies were included in this. I think they've come out of it some, but you see, because they're on the same boards with the petroleum product people, and those are on other boards and stuff, they wind up trying to protect each other. And indeed, they kind of do that, okay? And you can't have a lot of innovation when everybody's trying to cover their own backsides, okay? So, don't talk. That's probably more than I need to say. All right, that is the last slide in the book, in the chapter 3. And you'll hear me say this every chapter: nothing replaces reading the chapters. So please try to read the chapters. Better if you read it before I talk about it. That way when I talk about it, you have a context to put it in. But if not, read it afterwards or during or whenever, okay? Now, after you've read the chapter, there is a summary, and this one's one of the, probably a little on the short side, but it hits all the high points pretty well. Not all the nuances, but all the high points. Series of equations, summary of equations. There's 5 major equations they have there, so I'll let you read those. Probably one of the shorter lists of key terms for many of the chapters we'll have. Pretty short list there. They're given alphabetically, but they give the page numbers where they're first introduced or discussed or defined. But then applying the concepts. 36 questions, probably fewer than most of the chapters. Multiple choice. And if you know those, they give the answers for them. If you know those, you're probably in real good shape to do well on the test. Questions for thought, 12. That's probably a few fewer than normal. But for further analysis, 9. That's more than normal. Most of the time they're 4 to 6. Okay? So those are worth looking at too. And then the parallel exercises are more like the examples we had in the text. And if you have the big book, I know those answers are in the back. I don't know about the small books. I haven't found them in there, but I don't own a small book. The only ones I've had, students have given me, and then I've given them away again. I don't know if they're there. I asked them to put them there, but I couldn't find them when I had the book. So, any questions? Chapter 3. Okay, what does this mean? On Tuesday of next week, the last 30 minutes of class will be the Chapter 3 test. What we're going to do now is start Chapter 4 and get as far as we can. And if we've gotten far enough, which I think we will by 5:45, I think we'll be ready for the next lab. I've got it set up, kind of. I can't set up the lab because biology people use those labs. But I've got all the equipment in there. I think I have it all, knock on wood. But it'll be fairly easy to set up once we're in there. So if we cover enough material in Chapter 4, then we'll stop at 5:45 and do the first lab for Chapter 4. Okay, I think we'll have time to do that. Any questions on 3, though, before we leave? Everybody get everything they need out of that last slide? I forgot to ask. Did everybody get everything there? Yes? Okay. All right. Well, then let me get out of this one and go to Chapter 4. Chapter 4 is a really good chapter to follow Chapter 3 because Chapter 3 was energy, 4 is heat and temperature, which is a form, heat anyway, is a form of energy. Now, something a little different about Chapter 4, I don't know what the deal is here, but all the others have been white background with dark type. Chapter 4 is a brown background with white type. I don't know why they changed things up here, but they did. Maybe just for variety, I don't know. But Chapter 4 is dealing with heat and temperature. Are those the same thing, or heat, temperature? Not quite. They are related, certainly. They are definitely different measures of things, Okay? Here's the core concept, which is on your page 87. A relationship exists between heat, temperature, and the motion and position of molecules. Okay. Time out. When you see the word motion, especially from the last chapter, what should come to mind? Kinetic energy. Exactly. Motion is implying the kinetic energy of molecules, and when you talk about position, potential energy of the molecules. So we'll be, in some ways, dealing with that most of this chapter. Now, the other thing to notice here, relationship between heat, which we call a macroscopic phenomenon. This room may be too hot. Maybe that's why the window was open. I don't know. Maybe it's other reasons, okay? But it was pretty warm in here earlier today. As far as I can tell, it's the only room with heat in the whole building. Everybody else was freezing. My first morning class was too big for this classroom. We were down the hall, freezing in that room. Just next door, the history instructor was freezing in there. I told her she could use this room because we had to move down the hall, okay? But, so there's certainly, that's a macroscopic concept. Temperature, macroscopic concept, something you talk about a room or yourself. But molecules, that's really a sub-microscopic concept. So a lot of what we're going to be dealing with is a relationship between macroscopic, what we measure, see, live in, and that kind of stuff, and microscopic, what's happening on way beneath our vision and understanding, what's going on at the molecular level. So here's the overview. We're going to be talking about thermodynamics. By the way, thermo means what? That prefix. Thermo. Heat. Thermometer. Thermal underwear. Okay? Anything that is relating to heat. Okay? Dynamic. What does that mean? Dynamic as opposed to static. Something's moving or changing. Okay? So the thermodynamics is the study of, here it is, the study of the macroscopic, the big scale things that we can see, processes that involve heat, mechanical and other forms of energy, and how they change and interact. Okay? Thermodynamics. Okay? Now the applications of this are these. Some. Systems with energy inputs and outputs. We'll talk about several of these. A heat engine, y'all work on them every day, some of you do, right? That's what an internal combustion engine is. It's using heat to move a car, to turn the crankshaft, to move. That's a heat engine, okay? There are others as well, of course. There's heat pumps. That's something like your AC. This isn't a heat pump, but it's similar to it in that it's pulling our upstairs in our house has a heat pump. Downstairs we have a furnace, but the upstairs has a heat pump, and there it's taking heat out of the atmosphere and moving it and pumping it inside in the wintertime. In the summertime, it's taking heat out of the house, this is air conditioning mode, and pumping it to the outside, okay? Then we have things, and a refrigerator is one of those that's taking the heat out and moving it elsewhere. All those kinds of things. These are applications of applied thermodynamics. Okay? Now these are based upon but not concerned with what's going on microscopically. These are macroscopic processes that are based on, but we don't really concern ourselves with the microscopic details going on. We'll talk about that a little bit later. This is just the overview. Here's their approach. We'll discuss the underlying microscopic processes. What's going on the molecular scale, okay, that produces heat, changes the temperature, that type of thing. Then we'll relate those microscopic with the macroscopic views, okay? And then we'll look at the laws of thermodynamics. Now, when you talk about the laws of thermodynamics, historically, traditionally, there's been three biggies, okay? We'll talk a little bit about the first two. The book hardly mentions the third one. I'll try to get it in there just to complete the deal. However, everything we're doing is based on, and they came up much later in time with another law that basically the first three are based on. And because they're based on it, they wanted to call it the zeroth law. Because if you named it the fourth law of thermodynamics, hey, wait, the others are based on that, so they wanted to give it a lower number. The book doesn't even mention that. I'll try to remember to bring that into play when it's there. It's something we all take for granted, but it's definitely a law of thermodynamics. So let's start with the microscopic scale. Did y'all get that? Did I need it? Was I too fast? Okay, sorry about that. Sometimes I get carried away. I think I'm talking so much. Surely everybody got it all, but I realize how much is on that slide. Got it? Just to lead into what we'll be talking about later. We talk about atoms and molecules. That's what we mean on microscopic scale. They mentioned here, I thought it must have been the last slide, the movement of molecules. That's what we're talking about with microscopic, okay? Basis on which everything else is determined. And some of this, whether you think about it or not, you know it's got to be true. What happens when you rub your hands together really fast? They heat up, okay? Why is that? Friction, okay? Friction produces heat. It's a macroscopic phenomenon that we're looking at, but it's happening because of what's happening on microscopically. Now, let's take a gas, the air in the room here. Why is it at different temperatures? Which is the chicken, which is the egg, that's tough to say. But it's because the molecules are moving faster. The more you heat something up, whatever it is, a metal, a liquid, a gas, or whatever, the molecules will move faster, okay? And we'll look at some of that in detail as we go through the chapter. So everything depends on what's happening at the microscopic scale, okay? What's going on with the molecules. Maybe this would be an okay time to mention what the zeroth law of thermodynamics is. This is just sort of a crude description of it. If this object here is in thermal equilibrium with that object there, that means they're at the same temperature. If they brought them together, there wouldn't be any heat exchange. Okay? And that seems so. And if these two are both in thermal equilibrium with the third one, then these two have to be in thermal equilibrium with each other. I mean, they're really simple, basic phenomena, but guess what? That's what our whole way of measuring heat and temperature is based on. So that's the fundamental law, the zeroth law. The others will follow from that. Okay? Ready to change? Okay. Everybody got it? All right, let's go to the kinetic molecular theory. Now, we're not going into detail about this, but let me give it to you, at least the overview. What's happening on the submicroscopic scale is the movement of molecules. This is what I was talking about before. And this kinetic means moving. Molecular means that's what this is moving. This is the theory that brings it about. It's a collective hypotheses, multiple hypotheses, about the particulate nature of matter and its surrounding spaces. Okay? If you make molecules move faster, they're going to produce heat. If you heat up molecules, they're going to move faster. I mean, there's two ways of looking at the same thing. The Greeks, I think we mentioned this earlier, were the earliest written ideas on atoms. There was a guy named Democritus, okay? He was probably a few generations before Aristotle. Aristotle became the big cat, that everybody followed, but before him there were many really good natural philosophers, and Democritus was one. And here's what and again, they did all thought processes. Here's what Democritus said. I think I've used this before, but I'll probably use it again. But here's what it is. He said, what if you had a piece of iron, and you broke that iron into two pieces? Take the smaller piece and break it into two pieces. Take the smaller piece and break it into two pieces. And just keep doing this and keep doing this and keep doing this and keep doing it until you're down to the very small. Keep breaking and keep breaking. He said at some point you get to the place where the smallest particle you can have that will still be iron, that, he said, would be indivisible. And the word in Greek for indivisible is where we get the word atom. Okay, in other words, as small as you can get and still be that material. So that was his idea, that there had to be some smallest particle. Of course, he couldn't produce it, he couldn't do it, he couldn't measure it, didn't have the technology to do that, but he thought through it and said there has to be some smallest particle, indivisible. You can't break it any smaller, so therefore he called it an atom, meaning indivisible. Well, a couple generations later, here came Aristotle. And Aristotle liked to think about things. He said, no. Material is a continuum. No matter how small you break it, you could break it smaller. It's just a continuum of nature. So, no, there is no atom. So people threw out the idea of atoms. Okay? Some did. Democritus' writing was still there. Okay. Now, let's come out of history into the current view. Now we know matter is composed out of submicroscopic particles, and we still use Democritus' name, atoms. However, today we know atoms have smaller particles in them. Those smaller particles will not be iron, they will be subatomic particles. Okay? So we won't get into that now. That's a whole new, different branch of physics. Okay? But the smallest particle that would still be that material is an atom. Okay? Kind of. Okay? I'm going to take back that a little bit because iron is an element. Smallest particle there would be an atom. But let's say something else, like part of the mortar that makes up the joints here, or even the concrete blocks, is a compound called calcium carbonate. Okay? Calcium carbonate is made up of atoms, but there's different kinds of atoms. There's calcium in there, there's carbon in there, and there's oxygen in there. Okay? The smallest particle of calcium carbonate is a molecule, not an atom. Okay? So that's what the next topic is, the next point, bullet point. Atoms combine to form molecules. Okay? So if you're dealing with pure elements, the smallest you can get and still be that material is an atom. But if you're dealing with most of nature, and even things man-made, then the smallest particle that still is that material is a molecule, not an atom, if it's made up of more than one thing. And most materials are. The desk, just about everything in here would be a composite of more than one thing. Most macroscopic, big-scale phenomena can be traced to what's going on the molecular level. Okay? That's why we call it kinetic molecular level, not atomic, but molecular, because we're dealing with the molecules. Okay. Did everybody finish that slide? Anyone still need that? Okay. Let's go to molecules. A much busier slide, smaller print. Okay. I've been hinting at this. Let me get back to the basics here. When you have your chemical elements, these would be the things you find in a periodic table. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, fluorine, chlorine, all those things. Those are your elements. They find by each unique type of atom. Okay? Any of those materials, the smallest you could get would be the atom. But when you combine two or more atoms together, like hydrogen and water, hydrogen and oxygen, you get a molecule of water. That's a compound. It's not pure hydrogen, it's not pure water. Pure hydrogen, oxygen. It's a pure substance made up of two or more atoms that are chemically bonded. And when I say chemically bonded, that carries a lot of meaning with it. And here's what I mean by that. Does anyone know, did I ask these questions before, what sodium is? If I asked that, okay. Anyone know what sodium is? You've probably never seen any pure sodium. It's what?
Metal.
It is a metal. It's a very, very soft metal. You would never think it a metal if you saw it. But it is a metal. Okay? A very soft metal. Sort of yellowish in color, if I remember right. And the only time I've ever seen it is in a chemistry lab in a jar, and it was under oil. That's why I say I think it was yellow, because the oil may have been yellow. Why is it under oil?
Reacted to oxygen.
Well, not just oxygen, especially water. If you let water touch sodium, you have a major explosion. Water creates an explosion because sodium reacts as a very, very, very reactive metal. That's why you never see pure sodium. It's already reactive with something. But when you have it in a chemistry jar, it's always under oil because you cannot let water get near it. If you were to touch a piece of sodium, you would immediately burn your finger. Why? Because you have water in your body, and it would suck out that water and leave a burn there. Okay? Because when it reacts with water, it gives off enormous amounts of heat. That's what I said, it's explosive. Okay? There's sodium. A yellow reactive metal, explosive around water. Okay? Anyone know what chlorine is? Probably know things that have chlorine in them, but does anyone know what chlorine is itself? It's a green, poisonous gas. Okay? Every now and then you'll see a tanker truck on the highway or a rail car, mostly rail cars, and they'll have all sorts of danger symbols on them saying contains chlorine. You don't want that car to ever derail. You don't want it to split and leak. If it does, people are evacuated immediately because chlorine is a green, very poisonous gas. All right. So here we have a yellow, soft, very reactive metal and a green, poisonous, very dangerous gas. Does anyone know what sodium chloride is? What?
Salt.
Yes. You probably had some on your food today. Okay, you may even have some in your drink that's on your desk. It's common table salt. Is it yellow and reactive? No. Is it green and poisonous? No. Is it a metal? No. Is it a gas? No. It's a completely different thing. So when you have two or more atoms that are chemically bonded, they make an entirely new substance. No characteristics of the previous material that make them up. Just like water. Hydrogen is a very explosive gas. Oxygen is the gas that's necessary to support combustion. And what is water used for? Putting out fires. Can you get any different than that? Okay? So yeah, when you have a compound, pure substances made up of two or more atoms, chemically bonded that have no characteristics or features of those individual atoms. They're a chemical creation. Okay. So compounds, that's a macroscopic concept. The microscopic elements are, that's not a good word, building blocks for compounds are what we call molecules. That's the smallest unit retaining the properties of a compound. Just like an atom is the smallest unit retaining the properties of an element. Element is the macroscopic, atom is the microscopic. Compound is the macroscopic, molecule is the microscopic representation of that. Okay? So, now here's a little shorthand that you have to keep in mind. When we're talking here about molecules and kinetic molecular theory and that kind of stuff, we're talking about either actual molecules or even atoms. Okay? There are about 6 gases that exist as monotonic gases. Helium, neon, argon, krypton, xenon, and radon. Okay? Those exist as individual atoms that just float around. They don't react with anything else. You never find compounds of those. They're called the noble gases. They're over on the right-hand side of the periodic table in that last column there. They don't react with anything. That's why they use hydrogen in blimps now rather than hydrogen, because hydrogen will explode. Helium will not. Okay? So all the blimps you see today have helium in them. Okay? Now, when you talk about a molecule of helium, you're talking about a single atom of helium. Most of the other gases that are not those 6 or 8 or whatever noble gases, they always occur as diatomic molecules. O2, H2, N2, Cl2 is the gas chlorine. They're always diatomic. So actually the molecule of oxygen would be 2 oxygen atoms. Okay? So molecule can stand for either atoms if they're monotonic molecules like helium, or molecules which are CO2, H2CO4, I mean, whatever you happen to have, molecules will cover both of them. Single atoms, pairs of atoms, conglomerates of atoms. Okay. So when we say molecular theory, it can be anything from a single atom to a fairly big molecule. Okay. Now, what are our molecular interactions? Most of the time, molecules are attractive. Okay, that doesn't mean they look pretty. It means they try to come together, cling together with each other. Okay, water is notorious for that. We've mentioned several times water is H2O. Hydrogen has a molecular weight of 1, or a mass of 1. So there's 2 hydrogens, that's a molecular mass of 2. Oxygen has a molecular mass of 8. Okay? And so water itself, H2O, no, it's 16. Okay, is 18. 16 from oxygen, 2 from hydrogen, 1 from each one. Okay? 18 is its molecular mass. You find any compound or element with 18 or even anything close to 18, it's a gas. Water ought to be a gas, but it's a liquid at normal temperatures and pressure, right? Why is that? Because water, remember, it has 2 hydrogens and 1 oxygen. Now, they don't do this. They don't do hydrogen, oxygen, hydrogen. Okay, they don't do that. Okay, they do hydrogen, hydrogen, and oxygen. Okay, so always 2 hydrogens are at one end and oxygen at the other end. The hydrogens tend to be positively charged a little bit more than the hydrogen, not oxygen. The oxygen tends to be negatively charged. There's a reason for that chemically. So therefore, we call water a polar molecule. Okay, and as a polar molecule, it's attractive because this positive end is going to attract to an oxygen. And that one's going to attract 2 oxygen. This oxygen will attract 2 hydrogens. They stick together like crazy. They are very attractive. They cling together. That's why water is a liquid at normal temperatures and pressures rather than being a gas. Because of that strong, what they call hydrogen bonding. Okay. Now, so they tend to cling together. That characteristic of clinging together is called cohesion. Think of cohesion as being stickiness, and they stick with each other. The attractive forces between like molecules. Okay? Water attracts water. Okay? And most molecules are attracted that way. Okay? Now, that's between like molecules. There are others that are called, another type of stickiness is adhesion. And this is attractive forces between unlike molecules. This would be like water wetting your skin. Okay? Water wetting the dog. You know how a dog has to really shake to get that water off, usually right in front of it. Okay? And they do really good with that too. But the water tends to wet just about anything. The glue mechanism we call adhesives because they tend to stick unlike things together. Same base of the word. So cohesion is the attractive forces between like molecules, adhesion, the attractive forces between unlike molecules. There are some interactions that are repulsive. For instance, you really want to make your car look good, what do you do? Look good. Wash it and wax it. Now, why is waxing the second step there? If you just wash it and then you splash through a mud puddle, the mud's going to stick right back to the car, right? If you wax it and then dirty water lands on it, it's going to beat up and roll off because wax and water are repulsive to each other. They are not attractive. The reason for that, the hydrogen bonding, water is a polar molecule, wax is a nonpolar molecule. Nonpolar and polar molecules just don't mix well at all. Now, what will break or mix with wax real well, and y'all probably have used some, is pretty toxic stuff, but be careful with it. Carbon tetrachloride, you ever run it? Carbon tet, they sometimes call it. They don't use it much because it is really a little bit on the dangerous side to use. It can cause cancers and other things. But boy, it will cut through grease like crazy. Okay? And I know there's some compound that y'all use in your soaps, right? That cuts grease really, really well. Those are polar molecules, not polar molecules. Okay? Everybody got this so far? Okay. Wow. Let me make sure I haven't missed anything on the movement here. There is a pretty interesting little graphic on your page 89, and we're going to get to that in the first thing we're talking about here, but that is a electron micrograph from electron microscope of a crystal of titanium niobium oxide, okay, magnified more than 7.8 million times. That has to be a electron microscope. Okay, so I think we've hit everything up to this slide. Phases of matter. I forgot to bring my watch in here, so y'all have to help me keep track of time. Okay, phases of matter. Back when I was in school, which was so many decades ago, I can't remember it hardly, we used to call them states of matter. They try to get away from that terminology now because once quantum mechanics came into being, a state means something else. So they call them phases of matter. First phase we'll look at is solids. Okay? A lot of what we see in the room here, solids. Okay? What does that mean? It means it has a definite shape and a definite volume. That chair has a definite shape. It doesn't change. You can move it around, twist it, turn it over and stuff, but it keeps its shape. Okay? It keeps the same volume. It's not expanding or contracting. It keeps its own volume. Why is that? Why is a solid have these characteristics? This gets to that graph I was pointing out. It has a rigid, usually three-dimensional structure. Okay? And what we mean by that, the atoms or the molecules are bonded into place. Once they're there, you can move them, twist them, and turn them, but just like you can flip the chair over, but you don't separate them. They are fixed in proximity to each other, but also relative to each other. They don't move. They're fixed in place. Yeah, they move, they vibrate, but that's about the only thing they do. The allowed motions are restricted to vibration in place. Okay? And that's all that happens. You know, just like shaking your foot. It's just vibrating, but your foot doesn't come off. It doesn't change. It's just in place. Atoms or molecules are bonded in place, and what we call that is a crystal structure. Okay? A crystal structure. Every molecule belongs in a certain position. And this is how they represent it here. This is two-dimensional, but if you had another one out here and here and here and here, and behind and all over the place, then these are fixed in place. They're allowed to vibrate. That's why they put spring-like things in between. They're allowed to vibrate, but they don't move past each other. They stay in the relative position to one another and the relative proximity to each other. The vibrations occur, yeah, but they don't have motion. That's what gives them the definite volume, shape, and volume. Okay, so I'm going to take back a little bit of what I've just said. If you heat up a solid, you probably won't notice it, but it does expand a little bit. And when it cools, it contracts a little bit. Very, very little. Something you can't see and tell much about, but it does. Okay? Anyone know any ramification of that? I'll give you a couple of them. One, what's characteristic of a train going down the track? What does it sound like? Typically. I mean, not the engine, that kind of stuff, just the cars rolling past. Sort of a click, 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 click. You heard that? What is that? Any idea? Okay. The steel rails that they're on are finite length. I don't know, 20, 50 feet, something like that. But they have some finite length. They couldn't just build a rail that goes miles and miles and miles. They have to have finite length. And where they join together, there's a little space, a gap. Okay? That doesn't sound like it's very efficient. Why wouldn't they put them right against each other? Especially if you're laying those tracks in the wintertime. Wouldn't that be a good idea to put them right next to each other? No. Because when the temperature changes in the summertime, if there wasn't that gap there, then something has to allow for that expansion. They warp. They bend. Okay? And occasionally, nothing recently, but back when they were first doing these things, you would have major accidents because people put the rails too close together and didn't allow for what they call an expansion joint. When you go over a bridge, okay, every bridge you go over, don't you usually hear a click at the beginning and a click at the end? What that is an expansion joint. If you look down at the road there, you'll see they're sort of tongue and groove type things. Because the metal in those bridges, in the summertime, they're going to heat and go closer together and expand. In the wintertime, they're going to contract and get further apart. Those are expansion joints. They have to have them. If they didn't, you'd have warping. You would have bridges falling down, you know. So they do expand and contract, but they keep their position. They keep their relative position. So the volume pretty much is the same. Very, very small changes in volume. Okay. Now, how do you make a solid into a liquid?
Melt it.
You what?
You melt it.
Melt it. And how do you melt it? What do you have to do to it?
You have to use heat to melt it.
But you heat? Is
Yeah.
that what you? Absolutely. You add energy to it. If you add heat to a solid, most solids, they will melt. Not all solids. Some solids will catch on fire. Okay, so you don't want to do that to them. Okay, but most solids, if you heat them enough, you'll actually melt. What are you doing? You are breaking some of these bonds between each other, and now the molecules are free to move past each other. That's how you go from a solid to a liquid. You add heat. Absolutely right. So this is what a liquid is. Still has a definite volume, but an indefinite shape. It takes the shape of whatever container it's in. What's the difference here? It only has weak cohesive bonds between the component molecules. They stick together, okay, but they don't stick in place. They stick in proximity to each other, but they don't stick in the physical location of each other. They lost that crystal structure, okay? The constituent molecules are mostly in contact with each other. They like to stay close by. That's what that cohesive bonds are. Now, though, you have vibration. They certainly can vibrate, but they can also now rotate. They can roll past each other. There's a limited amount they can translate, move in one direction or the other, okay? So that's somewhat limited, okay? How you got there? Added energy, added heat to that solid. Down the road here at the U.S. Steel plant, they heat up iron and other components and make that steel into sheets. They melt the steel, and then they roll it into sheets or into pipes or into whatever they want to do, and then let it cool again. So most solids can be heated enough to turn into a liquid, except those that actually catch on fire. So don't do that to them. So here's the representative molecules. Now these are diatomic molecules here, and they stick close together, but so the proximity is still about the same, but they can rotate, vibrate, and even move in one direction or another. That's what makes a liquid a liquid. Okay? Now, how is it you get? Oh wait, did I get all this? Yeah. Okay. Now, how do you get a liquid to become? What's the third state or phase? A gas. How do you get a liquid to become a gas? You add more energy or more heat to it. Exactly. Boil water. Okay. Again, some liquids are flammable, so be very careful if you're adding heat. But if you have gasoline and it's a hot day and you open the lid, some of that gas is going to leave as gasoline vapor. Okay. In fact, your gas cans quite often swell up, and when you open them, there's some of your gasoline as a gas. Okay. A phase, gaseous phase. So how you get a gas? You add more energy. Okay. Now, what's the difference between a liquid and a gas then? Phases we're talking about. The gas has indefinite volume and indefinite shape. Okay? If I were to have brought into the room here a bottle of ammonia and set it in the corner here and opened it up and then remembered I had something else I needed to get out of my office, y'all just wait here a minute. After a while, Melanie and Michael here will be tearing up, rubbing their eyes and stuff. Y'all may not notice anything for a little bit, but then after a while, you'll notice it. And if you leave it open long enough, the entire room is filled with that ammonia gas. Yes? Go back one? Okay. Okay. And by the way, I mean, you're welcome to do that, but all these PowerPoints are out there on Blackboard too, so you can get them that way too. Yeah, but you're welcome to take the pictures of them too. That's fine. And they'll be in YouTube videos as soon as I get it uploaded tomorrow sometime. So, but yeah, you're still welcome to take the pictures. Okay, so here we have gases, indefinite volume, indefinite shape. Like I said, that ammonia would literally fill the entire room. Okay, if a lady comes in with a lot of perfume on, soon everybody in the room knows she has a lot of perfume on. It doesn't just stay right at her; it fills the entire room. Okay, we had some people in our house. One of the candidates, they got bumped out of the headquarters because everybody else was wanting to use the headquarters on Tuesday, so we let them use our house, and it was mostly women, I guess, that were in there. I know of one guy, there may have been others, but when I got home Wednesday night, there were still a few there, but you could just tell almost what each one of them was wearing, not quite, but yeah, it was, you could tell they had variety of odors on it. Okay. So now here with the gas, the molecules are not in contact with each other. In a solid, they're not only in contact with each other, they're fixed in place with each other. With a liquid, they're real close to each other. Proximity is close, but they are fixed in position. In a gas, nowhere close. They just fly around wherever they want to. No proximity at all. Mostly not in contact. Now, every now and then they do bump into each other and then they bounce right off. Okay? They don't tend to stick together. So what are their allowed motions? They can vibrate to their heart's content. They can rotate to their heart's content. Okay? That's if they've got more than one atom. Okay? And they can translate. They can move anywhere they want to in any direction they want to. They're not held by anything. Mostly free paths. Random free paths. Okay? This is how they represent it. Now here they show them as monatomic, one atom. They should be others. You see they're just all over the place. They're not trying to stay close to each other. They don't care where the other one's going. They're going any direction they want to go. Okay? So that's what a gas is. Now, there is one more phase of matter our book doesn't mention. Anyone know what that is? Plasma. Okay. What is a plasma? How would you get from a gas to a plasma? Yes. Add energy to it, absolutely. Okay? And what happens then when you add more energy to a gas, these molecules are free to do whatever they want to. The atoms are free to go anywhere they want to. Add more energy to them. What you actually do is you start separating electrons. Now, we haven't talked about how atoms are built, but you have a nucleus, which has protons and neutrons in them, really tiny, but very, very, very massive. And then a cloud of electrons with almost no mass whatsoever, a little bit, very, very little, taking up lots of space. Okay? And because of that, you add more energy, you can knock off electrons or gain electrons. One or the other. You just start exchanging electrons. Well, when you have an exchange of electrons, either a deficit or an excess, now you no longer have a neutral atom. You have what they call an ion. And when you have ions, now you have a plasma. Okay. Are there any ions in the room, you think? Where? You think there must be some somewhere. There are some. Some pretty obvious ones if you think about it. Okay? In the fluorescent tubes. If you know anything about fluorescent lights, you know there's a big old box somewhere in there, maybe not as big as they used to be. It's called the ballast. You're familiar with that? What that basically is a huge capacitor. Or a capacitor of some size. Okay? What a capacitor does is build up large amounts of charge and potential difference. Okay? And that large potential difference ionizes the gas that goes flying up and down those tubes like crazy. Okay? And when it flies past that white powder, have you ever seen a broken fluorescent tube and that white powder that's inside? That's called a phosphorescent material. That when ions go past it, certain ions at certain energy levels, it makes the electron jump up a level when it goes by. It picks up the energy and jumps up a level. Then when it passes, it falls back down again. Well, that energy difference from when it jumped up and fell back down, that's a photon of light. That's what produces the light. And a filament bulb is a filament that you're heating so hot that it glows. So most of the energy in an incandescent light is producing heat, not light. Yeah, some of it produces light. But in the fluorescent tubes, it's just jumping up energy levels and coming down. That's why that's a much cooler form of lighting, and it's a more efficient form of lighting. There is a cost to it, of course. That vapor that runs up and down is a mercury vapor, or it used to be. And mercury is a pretty toxic materials, so waste from that and actually building of those things. Most of it done in China, but there has to be some places in China that are pretty polluted because of that. Okay. Now, the newest form of lighting, anyone know what that is? LED lighting. And what is that? What does LED stand for? Light emitting diode. Okay? And what that is, a diode is a certain electrical component that when you put the juice to it, it gives off a wavelength of light. Okay? And there are several different kinds of diodes. The original one, I think, was red, wasn't it? First light emitting diode they developed was red. Later they developed a green light emitting diode. Well, you couldn't make a light bulb out of red and green light. You can make Christmas lights out of red and green light, and in fact they did. Okay, some of the early LED lights were just Christmas lights, reds and greens, separate. But then finally, I can't remember where the scientists were from. It seemed like one or two were from the U.S. and one maybe from Japan or somewhere, but they developed a blue light emitting diode. Once they did that, you could combine the three of those in one source, it produced white light. So once they got the blue light, then they had a means for doing that. Those are much more efficient than incandescent, more efficient than fluorescence, and not nearly the toxic components that fluorescents have. So by far the best choice. Least amount of heat produced. You don't have the big capacitors in them. That's the way to go. They're more expensive today, but hopefully in time they will get cheaper. In fact, it's harder and harder to find incandescent light bulbs anymore. Most places don't carry many of them. Okay. They're either compact fluorescent CFLs or LEDs. So that's what a plasma is. It's a energized gas that actually becomes ions. All right, now here's a question. Let's consider the universe, okay? What do you think the most common phase of matter in the universe? Solids, liquids, gases, or plasmas? Gases? Is that what you said? Not a bad guess. But most of space, remember, is not gas, it's just empty space. What is most of the material in the universe? Just think of our solar system. What's the biggest object in our solar system? The sun. It is at such incredibly high temperatures, because we have all those nuclear reactions going on there constantly, that just about everything in the sun is a plasma. No way it could be a solid or a liquid at all, not even a gas, it would be a plasma. And if you took our solar system, that's the sun, all the planets, all the moons, all the asteroids, all the meteors, all the everything in our solar system, the sun is like 600 or 700 times bigger than all the rest of it put together. So yeah, most of our solar system is a plasma. Not a solid, not a liquid, or even a gas, but a plasma. So, but that's just a side. That's not part of this chapter. Okay, sorry about that. Not really. Okay, so let's look at some of the molecular motions you have. Okay? Not at the motions, but at molecular motion in general. Characterized by the average kinetic energy of a large sample. Okay? In this room is filled with gas molecules. Some of these gas molecules are moving slowly, some are moving quite rapidly. There's every speed imaginable just about in this very room. Okay? What it's characterized by is what the average kinetic energy of the room is. That would determine the temperature of the room. If you close the windows, turn on the heat, then the average kinetic energy would increase. If you left the window open tonight and the temperature drops, the average kinetic energy would decrease. So temperature is a measure of the average kinetic energy of the molecules making up the substance. Now, I was talking about the room. If you're talking about that desktop, the average kinetic energy of that desktop would determine the temperature of the desktop. Okay? Now, this is proportional to the average kinetic energy, right? Measure the average, so it's proportional to it. Okay? They don't give the formula for it, and I'm sort of glad they don't, but it has kinetic energy, remember, is 1/2 mv squared, so that 1/2 relationship and this v squared relationship is all in there. Now, let's say that I took that bottle of ammonia in the corner here, and I said I left it, and it would take a while before it sort of filled the room. Unless, of course, I put that bottle of ammonia on a hot plate right before I left the room. What you reckon then? Say again?
Instant.
Yes, it would. The diffusion of that gas would be very, very rapid because you gave it more kinetic energy. The gas molecules move more quickly. So that's one evidence. Gas diffuses more quickly at higher temperatures than at lower temperatures. Okay. When you're dealing with solids and liquids, expansion and contraction, but also with gases too, with increasing and decreasing temperature. I think I told you, did I not, about the basketball left outside overnight in Nebraska? It was pretty cold. The kid I was doing some things with, he thought he had punctured his ball because it felt flat the next day. I said, nah, just put it in the house for a while. We did something else. We wanted to shoot some hoops. Couldn't. Put it in the house. About an hour later, so go get the basketball. Oh, no, it's flat. Don't you remember? You wouldn't let me pump it up. Go get the basketball. He went to get it, and sure enough, it was that. Expansion and contraction with increasing or decreasing temperature. Other evidence that the temperature is proportional to the average kinetic energy of the gas, or the liquid, or the solid, or even the plasma. Okay? Now, a guy came up with a pretty incredible experiment. I believe his name was Fizoux, Fizous or something like that. A really strange name. I think he was French. I'm not sure. But he came up with this idea that he was heating probably carbon, okay? Graphite, carbon, like soot. Heating some of this in a box over here and keeping it as close to just heating it up, and then sent that beam of carbon through parallel plates, so it came out as a very fixed beam. And he had over here a drum that was turning. I don't know what speed, but it was turning at some speed, so it was all set up. But that drum was solid except for one little slit in it. Okay? So most of the time, this carbon that was coming through into this beam, flat beam here, it would hit the drum on the drum. That would be it. Except when the slit came up, and then it would enter the drum. Now, on the inside of that drum was a photographic material that when the carbon hit it, it turned black. And when the carbon didn't, it was still white. So as it was turning, the faster molecules hit it sooner, and the slower molecules hit it later. So you had a distribution, and this is what the distribution looked like. At the very ends down here, very few molecules hit. These would be the faster molecules, these would be the slower molecules, and the vast majority would be about the temperature, represent the temperature that gas was being heated to, or that substance was being heated to. So this would be the distribution of the molecular speeds at room temperature. Okay? Now they just have some speeds here, but this is numbers. You see, most of them, this determines the temperature. Some of these are very cold molecules, some of them are very hot molecules, but the average is what we measure as temperature. Now, what he did was then increase the temperature of the gas, and this thing moved over here. Decrease the temperature, and it moved over here. So he could tell that by changing the temperature, he changed the distribution. Now, the speed of the drum stayed the same, of course. Otherwise, that would have messed everything up. All right, put it. putting a different film in there and running at a different temperature from the source, he saw that the peak moved this way when you cooled, that way when you increased the temperature. Okay? Indicating the heat was related to the average kinetic energy because that's the speed of the molecules. Pretty clever experiment. All right. I keep forgetting to turn the pages here. Let me make sure I haven't missed anything important. There's a little concepts applied on moving molecules. And it's sort of the same type thing I was talking about in the basketball. Blow up a balloon, okay? Get it nice and tight and blown up, and tie it off real good so the air can't come out, and then put it in your freezer. When you get it out of there, you'll see it's a limp noodle, okay? Let it sit in the room a little bit longer, and you'll see it becomes blown up balloon. Okay. Now, temperature. We almost have hit on, in fact, we did hit on it before. What is it a measure of? It's a measure of the average internal energy, think kinetic energy, of an object. Okay? Now, what do thermometers measure? Any idea? Okay, we say temperature. No, they're scaled for temperature, but it depends on the thermometer. Okay? One of the earliest thermometers, I think, was developed by Galileo. And what he did, he took, I don't know if you remember in chemistry lab sometimes, these beakers that were big and round with a thin, narrow neck on them. They have a name, I can't think of what it's called. It's not an Erlenmeyer flask, it's some sort of flask. And what he did, he put a certain amount of water in there and then flipped it over into a pool of water in a pan. So you had water in the neck of that beaker, but air up at the top. Okay? Now, then he marked and graded, you might say, the neck, and then measured. When he heated the air, or when the air got hot, the air expanded and pushed the water down. And when the air cooled, it shrunk and the water came up. That was the first thermometer. Was he measuring temperature? No, he was measuring the expansion and contraction of air because of changing temperatures, the average kinetic energy of air. That's what he was measuring, which you might say, in a sense, was temperature. How about those thermometers you hang on the tree outside? You don't do anything analog anymore, do you? But you've seen them, and the needle moves this way. When it's hotter, it moves this way. When it's cooler, it moves that way. What moves the needle? Does anyone know? What's that? There's a little mouse in there or a hamster that says, oh, it's warmer, I'm going to move the needle. No, not that. Have you ever heard of a bimetallic strip? Okay. Have you ever seen the inside of a, not electronic thermostat, but the old conventional thermostats? Ever looked at those? See a foil? Have you seen that? The needle is on the foil. That's a bimetallic strip. Okay? I think this is going to show one here. Yes. Okay? You have iron on one side and brass, say, on the other side. Two metals. Flat, right? Now you heat that up, and what happens? Well, both the iron and brass will expand a little bit, but brass expands more quickly than iron does. So what you have is the bending on the strip, because you have two different metals. The iron's not heating as fast as the brass, so the brass curls up on it. That's what moves the needle in your thermometer. It's a bimetallic strip in a coil, because this is a lot of change here. And in a coil, so you have a longer length of it, and as it heats up, moves that. So what you're measuring is not temperature. It's scaled for temperature. What you're measuring is the expansion and contraction of the bimetallic strip. Okay? These are thermometric properties. That's what you're using. So thermometers are used to measure temperature, but you're really not measuring temperature. You're relying on the different thermometric properties. The expansion of a gas, the difference in expansion of a bimetallic strip, or something else like that. Now, I bet you, I know that they used to have in cars. I think they still do. Anyone ever hear of a thermistor? What is a thermistor? It's actually a resistor. It measures resistance, but resistance changes with temperature. So therefore, you're measuring resistance, but you're calibrating it for temperature. That's what a thermistor is. Okay? Let me mark Dimitri here. Has anyone else come in since I called roll? I want to make sure you're here if you are here. Okay. Now, anyone ever hear of a thermocouple? Yay or nay? Okay, a thermocouple is basically two wires or electrodes or something, and the conductivity of that is influenced by temperature. So what you're actually measuring is the conductivity of how much charge is being transferred and through that couple, okay? The coupling of the two metals there. So you're measuring these thermometric properties, but you're calibrating it to temperature. So the bimetallic strips and the thermostat. And this is how thermostats work. You know, what a thermostat has in it, on that bimetallic strip, it has a pool of mercury. And when the thermostat gets to, the temperature goes up in the room, it tilts this way and the AC will come on. Or if it tilts this way, the heat would come on. Or the AC would turn off or something. So that's how a thermostat works as well. All right. In your text on page 91, there's a picture of the inside of a thermostat, and you see the bimetallic strip there. You can't tell it's a strip, but it's in a coil there, and that's what's, let's see if I can see the mercury pool. Yeah, the mercury pool is up on top. It's in a glass vial. Yeah, they even list it there, mercury vial. And if the bimetallic strip tips it a little bit, then it's going to connect a electrical circuit, turning on the heat or whatever. And then when it gets hot enough and the bimetallic strip goes back, then it shuts it off. Or vice versa, whichever way. All right. Now we get to the temperature scales. Before that, there's a thing, I used to do this as a lab, but it just got so messy and it wasn't really all that accurate of a lab either. But it's, how good is the human body as a thermometer? Do you think you can judge temperature pretty well? Probably not. What we used to do, I actually did this for a few years, then I finally gave up on it. I would have a pan of pretty warm water, not hot, not to scald anybody, pretty warm water, and another pan of ice water, okay? And I'd have the students put this hand in the hot water and this one in the ice water, and they had the thermometers sitting in the water right there, so they knew what temperature these waters were. And then I had two more pans of unknown temperatures. I had them put their hands, take them out of the ice and hot water, and put them immediately into the other pans, and then estimate the temperature. They knew what temperatures these were, what were the temperatures of those. And generally, what would happen, they would estimate this second pan here that the hot water hand went into as a really low temperature, and estimate the pan that the ice water went into at a much higher temperature, because it felt pretty hot. Generally what this deal was, those two pans were at the same temperature, but hardly ever did anyone guess, oh, these are the same temperature. Because, see, your body got used to one temperature, you moved to the other, and it felt either excessively warm or excessively cold, whichever. So, yeah, your body doesn't make a very good thermometer, okay, in general. All right, let's look at the temperature scales. Now, there's some history here, as there is in just about everything. As I said, one of the first thermometers was done by Galileo. it was that air in the beaker, and as it expanded, it pushed the water down, and it fueled it contracted. So he was measuring air temperature by how much it pushed water back and forth. There was a major problem with that thermometer. Anyone guess what it might be? It didn't just measure temperature, it also measured barometric pressure. Because that's what a barometer does. If the outside pressure increases and the water is pushed up into the tube, and he didn't know anything about changing barometric pressure, but he knew his thermometer didn't work the same on all days. And when barometric pressure was high, it pushed water up and compressed the gas at the same temperature, or when it was low pressure, it would move out at the same temperature. So he had a problem with it. Well, who followed Galileo? Isaac Newton. And Isaac Newton took Galileo's idea, but he put it in a sealed tube that wasn't exposed to the air, so it couldn't experience barometric pressure differences, so it just was measuring temperature differences. Okay? But the thing is, the liquid in there has a much smaller coefficient of thermal expansion than air does. Air expands and contracts big time compared to a liquid. So now to get very much measured temperature, you had to have a very tiny, tiny little capillary tube, and that's what the liquid went up and down. We found out one of the best liquids for it was mercury. Okay, but then later they started using colored alcohol, and it did pretty well too. Well, that was Newton's contribution. Newton needed some sort of numbers, so what he did, he took freezing point of water, and he made that 0 on the scale, and then he took body temperature and made that 100 on the scale. Well, he actually didn't make it 100. He made it, let me see if I can remember. Seems like he made it 12 on the scale. Yeah, made it 12 on the scale. So he numbered from 0 to 12, freezing point to body temperature. Okay, and he had 12 degrees. Okay, well, those are pretty big degrees. And after people got a bit better at it and needed better precision, they started doing half degrees. And then they did quarter degrees. And then they got down to eighth of the degrees. Okay? When they got down to eighth of the degrees, they said, this is really what we should have been measuring all along. So 8 times 12 is 96. That was his body temperature. 96. Okay. So that was ultimately. So they quit calling them eighth of degrees, they just started calling them degrees. So now the scale went from 0 to 96. The 96 being body temperature. Well, along came a German guy named Fahrenheit. He didn't like this, even the refinement of Newton's thermometer, because in his lab, he was doing something that we used to do a lot in the summertime here in the South. I don't think we do it as much anymore, but has anyone ever made homemade ice cream? Yay or nay? You have. How do you do it? Not all the recipe and stuff, is that proprietary, I don't need that. So how did you get the cream to freeze?
Ice and salt.
Say again?
Ice and salt.
Oh, why salt? Okay? Yes, exactly. What salt does is depresses the freezing point of the ice and the melting point of the ice. So you get your temperatures to be much colder. Well, that's what Fahrenheit did in his lab. He was experimenting with different types of salt adding to the ice. And, Newton and others had been using the freezing point of water as 0. Well, now he was getting temperatures below 0. And he didn't like negative temperatures. So he said, no, I want my 0 to be as cold as I can make the salted ice in my lab. So he made that 0 on his scale. that moved the freezing point of water up to 32, and body temperature was still there somewhere around 96. Okay, you got that upper limit. Now it's 98.6, but in the ballpark there. So that's where the Fahrenheit scale came from. Okay, he wanted it as cold as he could make it with mixtures of salt and ice. Not that he was making that much ice cream, but that's what he was using in his lab to get cold temperature. Well, here came Anders Celsius from, I think, Sweden, or Norway, one of those Scandinavian countries. He said, no, this is crazy because not all labs use the same salt combination as Fahrenheit does. We need a more definitive scale that doesn't depend on anybody's lab, and it doesn't depend on body temperature, okay? We need something that's more fixed in nature. So he went back to 0 being the freezing point of water. Guess what he used as his upper scale? Not the freezing point of water, but the boiling point of water. The boiling point of water became his 100. Now, originally, he just called that scale the centigrade scale because he used 100 degrees between the freezing point of water and the boiling point of water. Whereas Fahrenheit had used 0 to be as cold as he could go in his lab, up to 96 or something like that, which is body temperature. So that's why the scales are so way off from each other. What is the boiling point of water on the Fahrenheit scale? Anyone know? Oh, you will. 212 degrees Fahrenheit. That's what the boiling point of water is. Okay? Well, along came William Thomson. Whoa! Why does this say Kelvin? William Thomson was a great scientist. In fact, he's largely the one attributed to the 3 laws of thermodynamics. I mean, he's the honcho in this field, okay? But, in addition to being a brilliant scientist, and this is really unusual, he was also an aristocrat. I mean, a really high aristocrat from a very wealthy landed gentry family. And those people were called either dukes or earls or this, that, and the other. He was Lord Kelvin. So that's where the name came from. Not his name, William Thomson, that's pretty plain, but Lord Kelvin. That was his title. So he came up with another scale. And he said, guess what, team? 0, the same problem that Fahrenheit had with it, the freezing point of water just isn't cold enough. It isn't. That should not be a 0. Because many of these formulas and equations we were talking about, when you're squaring things and stuff, you can't have a negative temperature if you're talking about kinetic energy of gases, because kinetic energy can never be negative. It's 1/2 mv squared. And when you square a velocity, you get a positive number. So we need to have a scale that never goes negative. And that's why Fahrenheit hadn't liked it either. So what Kelvin did, Lord Kelvin, and he wasn't the only one, but he contributed to this. They were studying gases, okay? We've already said, when you heat a gas, it expands, and when you cool a gas, it contracts, right? So what they did, they studied several gases, and they had their scale here, and they had temperature on the horizontal scale and volumes on the vertical scale, okay? So it had a certain volume of gas here, a certain type of gas, and then cooled it, and its volume decreased some. Cooled it, and it decreased some more. Cooled it, and it decreased some more. Cooled it, and they noticed this was very close to a straight line. It was, in all practical purposes, a linear scale. Okay? Now, at some point down here, if you cool the gas enough, what does it do? It becomes a liquid, and almost all its volume disappears. Right? Just like heating a liquid makes it a gas, cooling a gas liquefies it. So after a while, all these gases then went almost to 0 volume because they became a liquid. Okay? But while they were gases, they had almost a linear scale here. So they did a different gas, and it may have been like this. And a different gas could have been like that. But they looked at all these gases, and all these scales, and they were all pointing to the same place down here. They never got there because they all became liquids, okay? And ultimately, they would all become solid. We're not even going to go there. But they were all pointing toward the same scale. That point down there they called absolute zero. In other words, you can't get any colder than that. That's where, if the gas could remain a gas, its volume would actually condense to nothing. That's as cold as you can go. Because what can it do after that? Nothing. Okay? So that was called absolute zero. That's as cold as you can go. Okay? That's what Kelvin made the zero in his scale. And it's called the absolute scale or the Kelvin scale. Okay? So that's the history of these three. And they're all with respect to, WRT means with respect to the reference points. So Kelvin had absolute zero as his zero, but then he used Celsius degrees. Okay? The same size degrees that Celsius had used. Not Fahrenheit degree, those were different. Okay? Now, this is illustrating what those are. Okay? On the Kelvin scale, absolute zero is 0K. Now notice here, these scales all use degree symbols, Fahrenheit and Celsius. Kelvin does not. You never use a degree symbol for Kelvin. It's just 0K, 5K, 17K, 273K, 370, whatever. Just K. Okay. Now, zero, freezing point of water, is 0 on the Celsius scale. That's 273K. Okay? 273K. Meaning absolute zero, because the Celsius degree is the same size as the Kelvin degree. Then, in the Celsius scale, absolute zero would be minus 273 degrees Kelvin. Okay. The boiling point of water would be 100 on the Celsius scale. It would be 100 plus 273, 373K. All right. On the Fahrenheit scale, however, the freezing point of water is 32 degrees. Boiling point of water is 212 degrees. 0 Fahrenheit has no real meaning, but that's negative 18 Celsius to 55K. And absolute zero, of course, as I said, was minus 273 Celsius, minus 459 degrees Fahrenheit. That's cold. Okay. There is actually another scale, but I don't think anyone uses it anymore. That was zero here. It's using Fahrenheit degree size. And that was called the Rankine scale. R-A-K-I-N, I think it was. We used to have an employee here named Christy Rankin, but she was R-A-N-K-E-N. This was R-A-N-K-I-N, I think. But no one used it anymore. Okay. Now, here's the things to note about these scales, especially Fahrenheit and Celsius. What's the difference in temperature on the Fahrenheit scale between the boiling point of water and the freezing point of water? What's the difference there? Between 212 and 32.
I'm sorry. The boiling water means because the temperature is higher than the...
Absolutely. Boiling temperature is much higher than the freezing temperature. Exactly. Because you have to heat it up to boil it, right?
Yes, sir.
Yeah.
Once you boil hot water, it just...
You increase the temperature.
Up, but if you freeze it, then it decreases.
The temperature is going down. Exactly. Room temperature, by the way, is somewhere right around in here at around 70 degrees Fahrenheit, and that's right around 68 degrees Fahrenheit, which is 20 degrees Celsius, okay, which would be 293 K. That would be room temperature. So yeah, to boil water, you have to heat it way, way up. To freeze water, you do it way, way down. That's normal room temperature, okay? But my question was, what's the difference in Fahrenheit degrees between the boiling point of water and the freezing point of water? It's a simple subtraction. What is it? So again, between the boiling point of water and the freezing point of water. How many degrees Fahrenheit between those two? 180 degrees. Perfect. So 180 degrees Fahrenheit is the difference between boiling and freezing point of water. What's the difference on the Celsius scale? Even easier.
80.
Say again?
80.
No, between boiling point and freezing point of water, not room temperature. 100 degrees Celsius. Okay? Now those are the same temperatures. They're just on different scales. So when we're going to make our conversion between the scales, we have to keep in mind that it takes I'm going to change to a different color here. What color would you like? Some light color. Yellow, green, orange. Pick a color. Okay, y'all aren't picking anything. I'll pick yellow. Okay? So 180 degrees Fahrenheit is the same difference as 100 degrees Celsius. Okay? So what's that ratio? Say again? Reduce it. 18 to 10, or reduce. Say again?
1.8.
1.8 to 1. That would be 1.8 to 1, or 9 to 5, right? Right or not? Yeah, 9 to 5. Divide this by 2 and divide that by 9 to 5. Dolly Parton sang a song that way. No, okay, we won't go into that. Okay. That was a movie too, I think, wasn't it? Y'all wouldn't remember that. You don't even know who Dolly Parton is. Okay, never mind. Okay. Yeah, you do. Dollywood? Okay. Now.
Wait, excuse me, you said divide 18 and 10 by 2?
Yeah. What we did here to get the ratio of this, first I just wiped out the 0 and made it 18 to 10. Someone said that. Then divide each of that and you get 95. Or you can divide this by that and you get 1.8 to 1. All those are the same ratios. Okay, it depends on whether you get whole numbers or fractional numbers or decimal numbers.
So that means that we just divide 18 and 10, and that's the answer?
Okay, that's one answer. All these are the same thing. This is one answer. The ratio in simplest terms, whole numbers, is 9 to 5, and decimal number is 1.8 to 1. Okay? In non-reduced fractions, 18 to 10. Or 180 to 100. That's the original thing. But I just wanted you to remember this, because this is how many Fahrenheit degrees correspond to how many Celsius degrees. The 9 is how many Fahrenheit degrees to 5 Celsius degrees. There's a reason that I'm showing you that. And it's going to show up, in our conversion formulas. Okay, we're going to convert Fahrenheit degrees to Celsius, also convert Celsius degrees to Fahrenheit, and then we'll do Celsius to Kelvin. Okay, Celsius to Kelvin is pretty easy. Let's go back to our thermometers here. Here's the other problem we're going to have to deal with. I'm going to erase these for now because we've already used them. We'll come back to maybe that later. But here's the other problem. Number one, the degree sizes are different, and that's what this ratio is, 9 to 5, or 1.8 to 1. But the other difference is, where are you starting? This 0 is here, that 0 is there. So in order to get the same starting point, 0 degrees Kelvin Celsius is the same as 32 Fahrenheit. Just keep that in mind. Those are the same. So if we're talking about degrees above freezing, you have to get to freezing first. And on the Fahrenheit scale, it's getting 32 in there. Celsius scale, you just start at 0. And then you use your 9 to 5 or 5 to 9 here. So let's get to our conversions. Okay? To go from Celsius to Fahrenheit, that's actually this scale. Why they put them in different order, I don't know. What you first have to do to go from Celsius to Fahrenheit. Remember, it's 9 degrees Fahrenheit for every 5 degrees Celsius, so multiply by 9/5. Okay? And then degrees Celsius are going to cancel out, and that gives you Fahrenheit 9. These would be Fahrenheit degrees, but you have to add 32 because that's where you start from. Celsius starts at 0, the freezing point of water, whereas Fahrenheit, the freezing point is 32, so you have to add 32 to it. Okay? So you're starting from the same location. So that's the conversion between Celsius to Fahrenheit. Okay? Now we go the other way, Fahrenheit to Celsius. You first have to subtract the 32 from Fahrenheit, because that's 32 degrees Fahrenheit. Subtract that, and then you have 5 degrees Celsius for every 9 degrees Fahrenheit. Put 9 on the bottom, so the Fahrenheit cancels out, and then 5 times this. 9 into that, then 5 times that answer to give you degrees Celsius. Okay, so that's the Fahrenheit to Celsius scale. Now, the Celsius to Kelvin, let's go back and look at that. That's pretty easy. To go Celsius to Kelvin, add 273. Look at that. Every place, you just add 273. Add 273 to negative 273, you get 0 Kelvin. Add 0 to 273, you get 273 Kelvin. Add 100 to 273, you get 373 Kelvin. So that's pretty easy. The Celsius to Kelvin scale is just add 273. That's this one. Okay? Now, does that sort of make sense? Okay.
I'm still writing.
Okay. While you're writing, and this, by the way, is on page 93, equations 4.1 and 4.2, and then over on the next column is the Kelvin to Celsius to Kelvin, which is 4.3. But in between that are examples 4.1 and 4.2, so let's do 4.1. I'll use this space on this scale here. The average human body temperature is what? 98.6 degrees what? Fahrenheit. Okay? What is its equivalent on the Celsius scale? So here we're doing Fahrenheit to Celsius. So we're looking for degrees Celsius. Okay? They call it in the book T sub C. Okay? And how do you get there? Well, you're given T sub F. That's what we're given here. First thing we have to do is subtract 32 degrees Fahrenheit from that. Okay? Then we have to multiply a degree Celsius, degree Fahrenheit measure, degree Celsius measure over a degree Fahrenheit measure. So the Fahrenheits can cancel out, and you're left with Celsius, which is what we want. And I've drawn over it so many times, it's ugly, ugly, ugly. Okay, so let's get that to be degrees Celsius. Okay, and that's what we want on the other side. Well, what's the ratio, Celsius to Fahrenheit? 5 to 9, exactly. Okay, Dolly Parton's the other way, 9 to 5. Okay, so this is what we use. So our degrees Fahrenheit is 98.6 minus 32. Do that first, then multiply by 5 and divide by 9. Oh, goodness, I can't write today. Okay. Multiply by 5 and divide by 9. Okay? Well, first, what is 98.6 minus 32? 66.6. Ooh. No, never mind. Okay, we won't go there. All right. Now, if I don't have a calculator, so I'm going to do this in my head, or on paper, or on the screen. I'm going to divide 3 into this, and that'll give me 3 here, and this will be 22.2. Right? 3 into 6 is 2, 3 into 6 is 2, 3 into 6 is 2. I can divide 3 into that as well. 3 into 22 is 7. That would be 21. And 3 into 12 would be 4, 7.4. Okay? Multiply that by 5. And that would be 37 degrees Celsius. 98.6 Fahrenheit is 37 degrees Celsius. Okay? So, if you had a temperature of 100, say, you would feel like you were sick, right? On the Celsius scale, that would be like 38 or 39 degrees. That doesn't sound very hot, does it? Okay? That's just a different scale. Completely different scale. Okay? See how that works? That's how we use these conversion formulas. Okay? 37 degrees Celsius. They don't use the 0.0. Okay, 37 degrees Celsius. Because they had 3 digits here, but I don't know. Okay. Now, can I erase all this? Everybody got it? Okay. Example 4.2. A bank temperature display indicates 20 degrees Celsius. You must be in Canada, right? 20 degrees Celsius. Now that is, they tell us, is about room temperature. Okay? What is the equivalent temperature on the Fahrenheit scale? So this time we're looking for T sub F given T sub C. Okay? What we need to do is multiply this by some degrees Fahrenheit over some degrees Celsius, so you can cancel out the Celsius and wind up with Fahrenheit, right? Well, what's the ratio? Fahrenheit to Celsius?
9.
That's 9 to 5. Okay? But that just gets you up to 0 on Celsius. But what's 0 on Celsius? Freezing point of water? 32 degrees Fahrenheit. So you have to add that 32 to get you up to the Fahrenheit degree. Okay, so here's our formula. That's this one right here. So let's do it. 9 over 5 times 20 degrees Celsius. Then we're going to add the 32 degrees Fahrenheit to that. Okay, because this is degrees Celsius, this is degrees Fahrenheit. 5 will go into 20 4 times. 4 times 9 is 4 times 36 plus 32 is 36 plus 32 is 68 degrees Fahrenheit. So sure enough, room temperature on this.
Excuse me, sorry. So is that supposed to be a 4?
Yeah, I did 5 into 20 4 times.
Okay.
I was just doing it in my head because I don't have a calculator. If you have a calculator, just punch it in numbers. But I was doing it in my head or on the board on the screen. Okay, so sure enough, 20 degrees Celsius room temperature, right around 68 degrees Fahrenheit. That's about what we keep our house at. During the winter time, sometime in the day when we're in there, we might bump it up a little bit, but at night we drop it below that. But that's about the average that we would have at 68 degrees Fahrenheit. In the summertime, because I'm cheap, I like to get a little warmer inside, so I would love to get up to 78, but my wife wants to around 71 or 72, 73, something like that. So room temperature varies a little bit, depending on how much you want to pay for your gas. And sure enough, 68 degrees Fahrenheit is what they got. Okay, then we have Kelvin scale. And that leads to example 4.3. So can I erase this one? Yay or nay? Okay. Yay. Okay. A science article refers to a temperature as 300 K. No one except scientists really use K, but that's what they use. What is the equivalent Celsius temperature? We're looking for T sub C. how do we get T sub C from T sub K? Yeah. Look at this one over here, and we see that TK is TC plus 273, so to get TC, you subtract 273 from T sub K. Okay? And when you do that, subtract 273, what do you get? 27 degree, whoops. No, that's right, degrees Celsius. K, you never use degree, but Celsius you do. So let me clean up my act here a little bit. Whoa, that didn't clean it up, did it? All right, 27 degrees Celsius. Okay? And that sure is what they got. But the B part of that says, what's the equivalent Fahrenheit temperature? Uh-oh, do we have a Fahrenheit to Kelvin scale conversion?
We have Celsius.
No, we have Celsius. So guess what? How do you shoot a red elephant? No, I'm sorry, blue elephant. With a blue elephant gun, of course. So how do you shoot a red elephant? Anybody? Say again?
You don't want to shoot.
You don't want to shoot them, okay. Well, you're just tranquilizing, that's why I didn't say it. All right? You don't use a red elephant gun. Why buy a new gun for a red elephant? You swing them around by his trunk till he turns blue, and then you use a blue elephant gun. I mean, it makes sense, right? Well, when you are doing this, don't come up with a new formula to get from Fahrenheit to Kelvin. Get from, Kelvin to Fahrenheit, get Kelvin to Celsius, and then use the one you already have, the Celsius to Fahrenheit. So, the equivalent Fahrenheit temperature, if this one was 27 degrees Celsius, then you're trying to get to Fahrenheit, you're using temperature Celsius, what you have to do is multiply by so many degrees Fahrenheit over so many degrees Celsius to cancel out the Celsius. And what was that ratio? Fahrenheit to Celsius? Say again? The ratio Fahrenheit to Celsius. 9 to 5. And that gets you up to 0 Celsius. You need to get that to Fahrenheit, which is add 32. That's this scale right here. Okay? So you take your 27 and you do 9 over 5 times 27 and then add 32 to it. Okay? That's not going to be a very pretty number. It's 81 divided by 5, which would be 1/16 or so plus 32 would be approximately 48 degrees Fahrenheit. So 27, is that right? That doesn't seem right. No, 81. I'm going the wrong way. I didn't add, I subtracted. Wait. 81 divided by 5. No, I did 3 times 27. 3 times that would be 243 divided by 5. Okay. Sorry about that, folks. I'm trying to do this too fast. Let me clean this all up. Okay, let me get that. Okay. 9 times 27 would be 63. 6 and 18 is 243. Divided by 5 would be 48.6 plus 32. I can't write. 32. And that would be about 81 degrees Fahrenheit. Okay. 81 degrees Fahrenheit. Nice balmy temperature. Okay. Well above room temperature. Because 20 degrees Celsius is room. So 81. Still a pretty pleasant temperature. All right. Now, well, I don't need to erase this. I can just go to the next slide. Okay, and that's where we're heading. But before we go there, on the top of page 94 is a closer look, which is talking about goosebumps and shivering. And I'm not sure I agree with everything this guy says, but it's okay. It's a pretty good slide there. If you've ever wondered why when you get cold you get goosebumps, and I've heard some people call it something else, goose flesh. That just sounds worse. The goosebumps, what I've always heard it called. There is a reason physiologically why that happens, and also why you shiver. Well, the shivering makes sense. Your muscles are contracting and making you move, and that warms you up. So that tends to make sense. I'll let you read that. There's not anything too outstanding there. Okay. So now we're ready to go to heat. We've been talking about temperature. Now we're going to talk about heat. Okay. This is section 4.3. How are we doing on time? Oh, I forgot to bring my watch up.
5:35.
5:35? We've got 10 more minutes, so we can get going on heat. Okay. So what is heat? Well, we know what it feels like, but what is it actually? Now, I make the mistake a lot of calling heat a form of energy, but it's not. That's close but no cigars. It's a form of energy transfer between two objects. It's not energy itself, it's an energy transfer. Now, if you think back when I was talking about being in thermal equilibrium, if you had two objects, okay, say a water balloon that you filled with hot water and another water balloon you filled with cold water, and you brought them next to each other, the heat is what goes from the hot balloon to the cold balloon. It's that energy transfer between two objects, okay? In the real old days, now this is well before my time even, folks, so don't get anything touchy about this, how they used to, especially kings and princes and dukes and earls and those kinds of things, how the servants warmed their beds was by putting stones near the hearth all night long as the fire was burning, and then you took the stones in a canvas bag or something and put them in the foot of the bed before they went to bed to warm the bed up. Okay? That was heat transfer. A hot object to a cold object, and that was heat. The transfer, energy transfer between two objects. Now, you have external energy. That's the total potential and kinetic energy of an everyday sized object. That's what we call the external energy. Okay? The internal energy is the total kinetic energy of the molecules of that object. Okay? So this is total potential and kinetic, external energy, internal energy, and this is the everyday sized object. So what they're talking about here, if I had a bowling ball here and I threw it to Matt, okay, I would be giving it potential and kinetic energy as I threw it to him. Okay, he doesn't want me to, I can tell. Okay, so that would be external energy. I've given that to it. Internal energy is the total kinetic energy of the molecules in that object. So whatever temperature of that bowling ball was, that would be a measure of its internal temperature, internal kinetic energy. The external can be transferred to internal, okay, if that bowling ball, when I'm throwing it, it's going to be bouncing off a lot of things, like things, and as it does, it picks up heat. Then some of that external energy could transfer to the resulting in a temperature increase. That's probably a lousy example. Anyway. All right, so here's what we have going here. Here the gal is pushing the table across the floor. She's being real stubborn about it and pushing down on the table when she's pushing it across the floor, which really is going to make it make a lot of noise, which means it's going to be interacting, vibrating on the floor, which, believe it or not, is going to increase the internal energy of the table and the floor. If you had very sensitive thermocouples attached to the table legs and the floor down there, you would see the temperature does go up slightly above because of that friction that you're forcing on the table leg to the floor. You'd hear it, okay, because it makes noise when you rub it across the floor like that. Your external energy is the movement of the table. The internal energy is the vibration that is caused by it rubbing against the floor. Okay. So, is heat the same as temperature? No. This is a really simple definition. A measure of the hotness or coldness of an object. Okay, yeah. Actually, it's based on the average molecular kinetic energy of that object. What is heat? It's based on the total internal energy of the molecules. Not just average kinetic energy of the molecules, the total internal energy of those molecules. Kinetic and potential. Now, let's imagine that have a tub full of water here. Okay? Now let's say, give me a temperature for that water. Make up the number. 60 degree water. Tub full of 60 degree water. And over here I have a thimble full of 70 degree water. Okay? Now, which of these has more heat? The tub full of 60 degree water or the thimble full of 70 degree water? Here's a way to measure that. Let's take some shivered ice and put it in each of those. Same amount in each. What is that going to do to this? Drop the temperature big time. What would it do to the tub full of water here? Hardly change it at all. This has more heat. This has a higher temperature. So heat depends on how much of the stuff you have, not just what the temperature is. It does depend on temperature, but that's not the only thing. Okay? Here's their illustration of it. Here I have a liter mug of water at 90 degrees Celsius. Boy, that's hot stuff. That's almost boiling point. Here I have 250 milliliters, which is a quarter of that over here at 90 degrees Celsius. So if I was trying to get this down to, this is I've just made some hot tea, but I want iced tea. So to get this down to a nice cool temperature to drink, which will I need to put more ice in? They're at the same temperature, right? Same amount of ice? No, I got to put 4 times as much ice in this because there's 4 times as much water in that to have it to the same temperature to drink. Does that make sense? So heat and temperature are not quite the same thing. They're related for sure, but temperature is a measure of the hotness or coldness of the average molecular kinetic energy of the material, whereas heat is how much total internal energy the molecules have. That means how many molecules you got. A lot more molecules, you got a lot more heat. Okay. How are we doing now? 42. 3 minutes left. I don't think I can do that slide in whatever you said. So let's find, if I can find where I am on this. Okay. Okay, there it is. We're on page 95, the right-hand column, just about the top of the column, right up to the cups. Okay, so let's do a pause here. All right, I forgot to turn on the sound again. If you're reading the first page of your lab, page 147, that middle paragraph, variations in atmospheric pressure have a negligible effect on the melting point of ice, but have a significant effect on the boiling point of water. Water boils at a higher temperature when the atmospheric pressure is greater than normal. Why would that be? Why would that be? Okay. If you think about let's imagine a pot of water here, level top it here, and you got it overheat. Okay? Now, what boiling water does is the molecules gain enough energy so they escape. They heat up, they move faster. If anyone's looking at that, you see the water in there, you might see moving a little bit. Bubbles are forming. And it ultimately is going to start moving more. I can see a little bit of motion on the edges, don't I? Okay, so the water is moving in there. And what is happening, you see a little bit of steam coming out. I can see some against a Max dark coat, See a little bit of steam. What is happening is the water molecules are speeding up because you're heating them, and they're escaping. Now, if you have more atmospheric pressure on it, then it's harder for those water molecules to escape. So that elevates the boiling point. At a lower atmospheric pressure, it's easier for them to escape, so it lowers, I said it backwards. More atmospheric pressure raises the boiling point because it's harder for them to escape. Less atmospheric pressure lowers the boiling point so they escape more quickly, sooner, right? Have any of you ever done much hiking in mountain areas? I haven't. Okay?
I did once, but I fell on the road, roll down some hills.
Okay? If you have, you might remember when you're cooking your food, you have to boil it longer, cook it longer. And the reason is the water boils at a lower temperature, so it doesn't cook as hot, so you have to cook it longer to get it to, if you're boiling something in a pot, okay? That's the same thing that's going on here. So normal atmospheric pressure is also called standard, and by the way, please, let's not play with the thermometers, okay? A couple of them have been broken over the years, and those are not that expensive to replace, but I have to go through a lot of hassle to get them reordered. So if you could, just set them down and let them be still, okay? Some of those contain mercury, and you don't want to get mercury on. Yes.
May I get a man?
Okay. Okay. All right. So, reading on page 147. Okay. Standard barometric pressure is defined as the atmospheric pressure that will support a 760 millimeter column of mercury. Okay? An atmospheric pressure change that increases the height of the column will increase the boiling point by so much. So we have to get our 30.5 inches of mercury into millimeters of mercury. Excuse me. Does anyone know the conversion between inches and millimeters or inches and centimeters? Either one will work. Anyone know? Inches and centimeters. Anyone know? Okay. What's that? 2.54 is that. Okay. But which is which? Let's first put the units into place. We want to get from inches of mercury to millimeters. Okay. You said 2.54? That's the centimeters. Okay. So if we're going inches to centimeters, what unit goes on top and which goes on the bottom? Inches are over here. Here's inches. We're trying to get to centimeters. Which goes on top? Centimeters on top and inches on the bottom. Okay, everything's going to be mercury. And what did you say? 2.54 centimeters is 1 inch. Perfect. Okay, now we need to get from centimeters to millimeters. Okay, what unit will go on top and what's on bottom? Always put the units in the place.
Millimeter on the
Okay. Say that again.
Millimeter on top.
Millimeters on top and centimeters on the bottom. That way the centimeters will cancel out. Here the inches cancel out. Okay? How many millimeters in a centimeter or centimeters in a millimeter?
10 millimeters.
10 millimeters are in 1 centimeter. Okay? So if you got your calculators, 30.5 times 2.54 times 10. 30.5.
774.
Second.
774.7.
774.7. Let's just round that to 775, okay? 775 millimeters of mercury. Well, that's a bit high seeming. Someone do 30 times 2.54 times 10.
30.
Yeah, 30 times 2.54 times 10. No.
762.
752?
6.
62. Okay, that's right. Okay, we're right. All right, so our atmospheric pressure, and by the way, folks, let's start recording this. The barometric pressure on page 152, this is next to the last page, back side. Barometric pressure is, and if you will, you got a big block there, so put 30.5 inches of mercury somewhere in that block, but also put 775 millimeters of mercury in that block. Okay? 30.5 inches of mercury. This is on page 152. Barometric pressure is about the middle of the column there. Barometric pressure is 30.5 inches of mercury or 775 millimeters of mercury. Okay? Everybody got it? All right. Put it in both of the columns there, trial 1 and trial 2. In fact, we're going to rename those columns. One's going to be thermometer 1 and one's going to be thermometer 2. Okay? Now, each of the teams has 2 thermometers. Look at them. You decide as a team which one you're going to number 1 and which you're going to number 2. It's up to you completely. Okay? And just make a suggestion. Okay? That one has a red band on it. This one doesn't. Otherwise, they're identical. So name one on 1 and the other 2. Okay? Yours, how are we going to do it? Okay. All right. Everybody know how to number 1 and 2. Okay? On page 152, the top of the column says trial 1 and trial 2. You're going to change that to thermometer 1 and thermometer 2. Okay? Figure out how you're going to do it. Okay? Yours is easy. One of them's a big long thermometer, one's a short. So you decide which one which is. Okay? Now. Okay. What I want you to do is everybody take your 2 thermometers. Now you need to know which is yours. Remember what team you are and what your thermometer's numbers are. Okay, bring those thermometers back here to this table. Just a second. A little bit of water. Okay. And put your thermometers into the water. We're going to let them sit there for a while we do the next chart. Okay. Now the reason I put a little more water in there, the ice hadn't completely, or not completely melted. There wasn't very much water in the bottom, so I wanted enough so it would coat the ends of the thermometer. Okay? Now, what I want you to be doing is, now when you're measuring the temperature, here's what you do. Pick it up so it's off the bottom of the beaker, because that might be a little different temperature right on the glass, and then read the thermometer however you can. So come back and periodically read, and when you see that it's not changing any, then record that temperature. That's going to be and that will be recorded on the page 152, the observed melting point. Do one for thermometer 1 and one for thermometer 2. So after a while, I'm going to check it. Y'all can stay as long as you want to. After a while, I'm going to check your thermometer. Don't take it out of the water or get it off the bottom. Yeah, both of them are supposed to be in the water. Okay? Both thermometers are supposed to be in the water. Do I see a thermometer sitting over here? That's supposed to be in the water. Hey, gosh, both thermometers are supposed to be in. Both thermometers. What's that? Well, you're supposed to know the 1 or 2. The numbers are written on there. Yeah. Okay. Does everybody have both thermometers in the water? Yay or nay? Okay. After they've been in a while, check them, see what the temperature is, and then after a little while longer, check again. When they come to, so they're not changing any, you can record the observed melting point. For thermometer 1 and thermometer 2, you're supposed to know which is which. Be sure you got your number thermometer. Sure is slow.
It says 0.3.
Second?
One says 0.3.
One says 0.3.
Yeah.
Check it several times and it stays right there. Okay, check it several times to make sure it's stable at that temperature. Okay? And you said 0.3 degrees or 3 degrees? 0.3. Okay. I didn't know you could read that accurately, but that's fine. That's
No,
fine.
but like it's between 0 and
Okay,
1.
right.
So
Okay,
probably
that's fine.
0.3.
0.3 is fine. Right? You got the temperatures? Not while they're out of the water.
Well, I got it before I pulled them out.
Okay. You record them. Okay, you don't read the thermometer when it's out of the water. You have to have it in the water to read it.
It's 0.2.
Second?
0.2.
0.2, okay.
So it's tab 1.
What's that?
We have to write on tab.
Okay, you write thermometer 1 under trial 1 column and thermometer 2 under trial 2 column. Okay. Has everybody recorded both thermometers in the ice water? Yay or nay? Recorded them. Okay, take your thermometers and put them in the hot plate water. Okay? It's not boiling yet, but it will be boiling fairly soon. I hope. It's taking a long time to get done. Well, any more around Does everyone have both thermometers from your team in the hot water? Okay. Won't do any good to watch it. It's, wait till it starts boiling. Okay? I think I probably just put too much water in there. I wish I would get less. No, that's about as hot as it'll go. Okay, just about, looks like it's just about beginning to boil, right? You think the water is boiling yet? Maybe not quite. Is it boiling? Is it boiling yet? Okay. When you see your thermometers stop rising, okay. Oh, I've got a question for you. Let's think back on the ice water. Y'all put them in there and they came to a temperature. I said, wait a while until it comes to the same temperature. Do you think the ice was still melting, but was the temperature still dropping? No, at some point it stopped dropping. That's when I said leave it in there until it stopped dropping, right? So the ice was still melting, though, wasn't it? Okay? So remember that, because that question's come up later. Okay? When you think those are boiling, read the temperatures, and when they're stable, let me know what they are. Okay, and again, be sure you pick it up slightly off the bottom to read the temperature, so you're not measuring the glass temperature, you're measuring the water temperature. Just like you did with the ice water. Okay? When you think the temperature is stabilized, let me know. Okay, then measure both thermometers and record that on your table as well. Okay, wait. Okay, go ahead. I forgot to have you do the measurement error of the melting ice. Okay. Has everybody recorded the observed boiling point?
Yeah.
Okay. Now, I forgot on the freezing point or melting point, what was your measurement error? How do you determine measurement error? It's what you measure minus what the real should be. And what should be the melting point? Zero. So if you had anything other than zero, write down what you measured and subtract zero from that. Pretty easy subtraction, right? Okay. Now. I'll put one back in. Oh. Didn't do too well, did it? You got it. Y'all get the temperature. You read the temperature while it's still in the boiling water, right? So read it. Off the bottom and read it there. Yeah, well, it's not something you want.
That's a lot of
Wait till it comes to a boil. Okay, did everybody read this while it wasn't touching the bottom, while it was still in the hot water? Okay, it's right side up. Okay. Okay. When it comes to these words, it takes too long. Okay. It's probably there now. See what it is. What is it? Okay, I'll move up. Okay. Now. Okay, you've got an observed boiling point for both thermometers, right? All right. Now we have to do your deviation from normal. Okay? And that's where you use your 775 inches of mercury. And back on page 1, you notice there it says, atmospheric change that increases the height of column mercury will increase the boiling point by 0.037 degrees Celsius. 0.037 degrees Celsius for each 1 millimeter of mercury. Okay? Now that's each 1 millimeter of mercury above your 760. Right? That's normal atmospheric pressure. How far are we above normal pressure? 15 millimeters of mercury. So multiply 15 times 0.037. Is everybody listening? Multiply 15 by 0.037. Okay? Say again? Okay, you got 0.555? Let's just call that 0.6. That would be degrees Celsius. Okay? Now, and is that positive or negative? Positive. Okay? So your deviation from normal would be plus 0.5 degrees Celsius, 0.6 degrees Celsius. Deviation from normal is 0.6 degrees Celsius. So your accepted boiling point is 100.6. And your measurement error then will be the difference between what you measured and 100.6. Second? Yeah, that's the difference, yeah. Okay? What you measure minus 100.6. Okay. What's that? I would stand back if I was y'all, but
I did mine wrong on that. I was thinking, I was
don't touch that. Come back to that later. Okay. I keep losing my lab. Here it is. Okay. Okay. Has everybody filled out the whole page now, the whole table for both thermometers? There are different calculations for for both. The barometric pressure should be the same for both. The deviation from normal same for both, and the accepted boiling point same for both. But all your measurements, they vary by whatever you have, right?
Right.
Okay. Everybody filled out the table. All right. So where we go now is your procedure. Okay? What we did was verify the accuracy of the lower point. That's what we did the first. And that's why you subtracted to see what your measurement error was. So that was number 1 on page 147. Okay? Then on number 2, we didn't do quite this fancy a setup. We just had a beaker over the water, so we determined that. Okay? So you should have done everything down to page 149. And here's the first question. Okay, folks, are you listening? Here's the first question on page 149. Now think back of when you put the thermometer in the ice. This is why I asked you that. When you put the thermometer in the ice water, and I told you to check it and then go back and check it again, and when it finally stopped changing, right? Okay? The water, the ice was still melting because the room temperature is like 70 degrees in here, and the ice is at 32 degrees. So the ice was still melting, but the temperature, did it change or not? No. Now, we haven't gone in class why it didn't change. Let me explain that to you. We'll get to it next time, but we didn't quite get far enough for it today. When you have a phase, okay, when you have a phase, solid, liquid, or gas, right, or plasma, at a certain temperature, you add heat to it, it changes the temperature, right? But if you're at a place, at a melting point, or the boiling point of water, okay, at either one of those, if you add more heat, it doesn't change the temperature. It changes phase. The ice melts to water, or the water heats to steam, right? One or the other. So that's why the temperature did not change in the ice water, because the temperature doesn't change when you're at a phase change. It only changes when you're at between the phase changes, when you're changing temperature, right? Okay? Does that answer number 1 for you? Okay.
One more time.
Yeah, one more time, please.
Okay. All right. You answer the first part. Did the temperature change while the ice was melting? No. Offer an explanation for this observation. Okay? When the material is in a phase change, there is no change of temperature. And it was. The ice was melting into water. That's a phase change. No change of temperature. Okay? Now, we talked about earlier, number 2. Describe how changes in the atmospheric pressure affect the boiling point of water and offer an explanation. We did that earlier. Y'all answered it, so record what you understood from that. Okay. Are all of you through with our barometric pressure calculations? Yay? Okay. We're using their board, and I don't like to mess it up. And it's not erasing very well. Yeah. Okay. Okay. Number 3. Have y'all proceeded to that? What would you say? Account for any differences observed in the melting point and boiling point readings. What did but bless you. Bless you. Were both of your thermometers exactly the same? Just about, but not quite. What would you say the differences were to you two? Okay, yeah. Basically, these are old thermometers. They weren't very expensive thermometers. They're probably calibration errors. That's most of what we account for that. What's that? Well, I thought I just said it. Okay. Now, calibration errors. Okay, listen up, folks. All right. Okay. Let's hold off on 4 and 5 for a minute. Where it should be on page 151. Let's go to going further. Using the data from your better trial, okay? Thermometer 1 or thermometer 2, which one had the best precision, okay? Using your data from your better trial, make a graph plotting the Celsius temperature scale on the x-axis and Fahrenheit scale on the y-axis. Now let me show you how to align this. Align it as in a letter. The x is on the horizontal and the y is the vertical, so your Celsius is down here, your Fahrenheit up here. Celsius along the bottom, Fahrenheit along the side. Okay? Okay? Your Celsius will start here with 0 in the lower left corner, and it'll be 20, 40, 60, 80, and 100 on the far right, not on the far right, but going across 20, 40, 60, 80, 100. You won't need 120 or 140, but you could if you need it. Okay, your Fahrenheit scale. Okay? Give me what your maximum boiling point was with your better thermometer. Now, this is not the observed reading, but your, I'm sorry.
105.
You got up to 105? Is that one the better one? What's the other one? 100. Okay. So you'll be okay. Okay? Okay. How's that? Or good thing. I think you know. Gifts are appreciated, but I can't take cash. Okay. No. Okay. Now, on the Fahrenheit scale, okay, this is going to be a little tougher. Basically, I think what you have to do, put 0 at the bottom, 30, 60, 90, 120, 160,
No, 50.
150, okay, yeah, I knew I was off there. 0, 30, 60, 90, 120, 150,
80.
180, 210. So 210 will be up here. You should go a little above that. Okay? Now, we didn't measure anything in Fahrenheit, did we? So we're going to have to use our conversion formula to do the Fahrenheit. Does anyone remember how to do those?
Yeah.
How was it?
From which? What do you want to convert?
Say again?
From Celsius to Fahrenheit?
From Celsius to Fahrenheit.
So it's 5/9. No, 9 by 5.
Okay?
And
Degrees Celsius.
Celsius.
and then add 32. So did everybody hear that? Okay? So probably over here on your data column, okay? If everybody's paying attention. Everybody paying attention? Okay, on the data page, what I would do is probably at the bottom of the page where you have room to write, you're only using your best thermometer, the better thermometer, the one that's closer to 0 and 100. Okay? On that one, for your observed melting point, what you should do is the Celsius reading. Are you listening? Celsius reading. Are you listening?
Yes.
Okay. Times 9 divided by 5, and then once you get that answer, add 32. Right?
Right.
Add 32.
Add 32 after you do the dividing and the multiplying. Right? You do the same thing for the, where is it? Observed boiling point. Okay? Multiply by 9, divide by 5, and add 32. But be sure you do an equal sign before you add 32. Now, what kind of numbers are you getting for the melting point?
33.8.
That sounds reasonable. Did you get it, everybody? So does everybody have a Celsius reading? And by the way, when you get those Fahrenheit degrees, folks, are you listening? When you get the Fahrenheit degrees, put it up there. You have observed melting point in Celsius, put the observed melting point in Fahrenheit. When you get the, make the calculation on the boiling point, you already have the Celsius there, put your Fahrenheit in that same block. On your best scale, not on your worst, but on the best. The best thermometer, better thermometer. Okay? Now, okay. Okay. So you got your measurements, okay? So on your graph now, find your melting point on the Celsius scale, your better thermometer, and then find that melting point on the Fahrenheit scale. Now remember you did 0, 20, 40, 0, 30, 60, 90, 120, 150, 180, 210. Okay? That was your Fahrenheit. Celsius was 0, 20, 40, 60, 80, 100. Okay? So plot those 2 points. You only have 2 points. Plot those 2 points on your scale. Celsius Fahrenheit and Celsius Fahrenheit. Then, okay?
Yeah, so our first one will probably be about right there. Because you'll go to 1 degree Celsius and 33.8 degrees Fahrenheit. So our next step is 100
Okay.
and 210.
Okay, once you've plotted your 2 points, then get your ruler and draw a line between those 2 points. Right? The first line should be somewhere near the bottom left corner. Not exactly, it'd be up a little ways. And the next point will be somewhere in the upper right quadrant. Not too far up there, but somewhere up there. If you want me to look at your points, yeah, you look good. All right. Should be plotted. Okay, get your ruler. Draw your line. That's good.
Yeah, so 200 degrees.
Okay? Now, once you got your 2 points plotted, and you draw a line between the 2 points, use your straight edges, what you need to do is calculate the slope of that line. And what is slope? Rise over run. So basically, you can take the difference in your 2 points on Fahrenheit and the difference in the 2 points on Celsius, divide the Fahrenheit by Celsius. Right? Rise is Fahrenheit, run is Celsius. Has anyone calculated the slope yet? What's that? Okay. What was the rise? What was the rise? Yeah. Yeah, that goes on top. Yes.
Yeah. Where's 15? I got 1.78.
Area on the graph.
He said the difference in the two. Bottom one was at 1 degree Celsius and 1 over 200. So the difference in those two is 99. So that's going to be your run.
Rise.
And then your rise, we were at 33.8.
Okay.
And we went to 210.
We're awfully close to needing to move ahead just a little bit. This is the fun part. It's not really part of the lab, but it is a question for the end.
Yeah, I think our slope should be 1.78.
I'll be right back.
Yeah, look at that. You got 0.8. I got 0.7. So, yeah, we're right there. Yeah,
How do you get 1.7?
yeah, so
Is this a cold one?
Is this a cold rise or whatever? Is this a cold one? 60 water? And subtract 16 water.
Huh?
You got the rise and they got the run.
Okay. What I want you to do, we're going to come back to your calculations, but I need to do this for all my water boils away. At the bottom of page 151, listen up. We're going to come back to what you're doing now. It says wash an aluminum pop can. I'd already done it. We don't call them pop cans. We call them Coke cans, whether they're Coke or not. Okay, leaving a small amount of water in the can, which I did. Use tongs to hold the can over a heat source. It's been sitting on one. And is steam still coming out the top? Yes, good. Okay? All right. And I'm going to do what it says, and I want you to, number one, explain first, tell us what happens to the can when I turn it over. And number two, we'll be explaining it. You don't have to use Carlton's law and Boyle's law. Okay, can everybody see this?
Okay, so you can see.
Okay? Oh, wrong one. Yeah. I had it right here in front of me. I blew it.
Well, oh, sheets now.
Okay. Sorry about that. All right, I have to let it fall again. Here it is, right in front of me. I'll turn it over there. Okay. When it starts steaming again, let me know. Okay, get back to your graph. Sorry. Duh. Make sure there's
Yes,
water.
basically, because this is not here.
I can't spell.
And then you rise by your
All right, sorry about that. I turned it in the wrong beaker. Okay. All right. How's the graphs going? Okay. So on page 151, what was the value of your slope? Okay. What's the meaning of the slope?
The rise in temperature.
Okay. What do you mean by that? How did you get it?
Rise or run.
And what was the rise?
Fahrenheit.
Change of Fahrenheit temperature over
Celsius.
change of Celsius temperature. That's the meaning of it. Is how much Fahrenheit temperature changed compared to Celsius temperature. Did everybody get something fairly close to 1.8? Okay. Number two. What was the value of the y-intercept? Oh, wow. And what do you reckon that represents? Of what? In what scale? No. Fahrenheit. It was on the vertical axis, the y-axis. Okay? Now, number three. Okay, tell me when you see the steam start coming out of the can.
I see some heat waves and AC.
Was it too hot? Yeah, it's getting steam. What's that? What's that? Yeah, that's true. You put what was on yours, not what somebody else did. Okay, let's look at number three. Listen up. Listen up. Number three. The slope-intercept form of an equation of a line, and you see it there written on your page, but, okay, is y is equal to mx plus b. You've all seen that in math class, right? Y is equal to mx plus b. Okay? Where y is the variable in the y-axis, what it was in our case? What was your vertical axis?
Fahrenheit.
Fahrenheit, okay? It's a variable on the, and x is the variable on the x-axis. What was our horizontal one? Degrees Celsius. M is what?
Slope.
Slope of the line. So our slope was from number 1? 1.8. Very good. And B is the y-intercept, which was something. What was it? It's around 32, somewhere around there. So use that information to write the equation of the Celsius Fahrenheit temperature graph. Okay? So instead of Y, you put degrees Fahrenheit, right? Instead of M, you put what slope you had. You calculated number 1. Instead of X, you put degrees Celsius. And instead of B, you put your y-intercept, what you measured in number 2, what you read off in number 2. All right? Now, what is that equation? Does it look at all familiar?
Yeah, it looks about what we did.
What's that? That's exactly the conversion of Celsius to Fahrenheit, isn't it? Somebody told me earlier that slope was 1.8. We were using 9 to 5, which is 1.8. 9 divided by 5 is 1.8. So that's exactly what that equation was. So that's the meaning of the equation. It's the conversion of Fahrenheit to of Celsius to Fahrenheit. Okay, you want me to try this again? Okay, what? No, this is a variable. All right, gather around so you can see this. I'll try to do it right this time. Okay. Can everybody see?
Yeah.
Okay, is everybody looking? Okay.
Can you grab my headphones?
What happened? You can what? It exploded, didn't it? Why did the can crush? What's that? In terms of what we've been talking about. What's that? Okay. Did the hot air come out? Is that what you said? Any ideas? Okay, you're really right there. It's atmospheric pressure crushed again. Did you know you're under that much pressure right now? More than that, actually. Okay, but you got pressure in your body pushing out again, so that you balance out. Why did it do that to the can? Well, what is in the can to begin with? Well, boiling water. A lot of that water was in steam. You can see the steam coming out. Okay. When I flipped it over in ice water, there wasn't much ice in there, but it was a little bit. Now that cooled it so that steam condensed back to water. When it did, it took up much less volume. Your pressure dropped like crazy. Atmospheric pressure crushed the can. Make sense? And those laws we talked about, that Boyle's and Charles' law, you don't need to do that. But Boyle's law reflects pressure and volume, and Charles' law, I think, was the other one there, is temperature and pressure. So you don't need to understand. What's going to make your question? Okay, yeah. We didn't finish 4 and 5 because we wanted to catch up on the graphs. Okay? Can y'all answer 4 and 5? Number 5, you answer yourself anyway. I don't give you any input on that. Okay, number 4 is a decent question. Now, it's referring back to question 3, which was any differences that were in your measurements. Remember, we said those were due to calibration error. Well, what would happen if you hadn't checked the calibration and you did an experiment with these thermometers, especially the ones that were off a little bit? Then the results you would be reporting would be off a little bit. And your conclusions would probably be off a little bit. So you would get bad input, gives you bad output. Okay? Does that make sense? Okay. Now I'll let you decide number 5. But you need to answer it. If you don't answer it, you lose points. However you answer it, that's up to you. As long as we got an answer, that's what I'm looking for. Anyone have any questions, anything before I shut down the Screencast-O-Matic? Okay. Are there any questions before I shut down Screencast-O-Matic? No?
So we just
Okay.
answered on one.
What's that?
We just answered on the intersection inquiry.
Yeah.
That's one.
That's number one. That's what we did with the
Okay.
camp.
We're not doing 2 or 3.
What's that?
We're not doing 2 or 3.
Oh, 2 or 3, no.
Okay.
I didn't even read 2 or 3. I don't know what they are. No, we didn't do anything. No, we didn't do anything in 2 or 3. Have a good weekend. Stay warm. It's supposed to get quite cold this weekend.
I hope it smells.
I doubt it.
Yeah.
Oh, I was going to cut this off.